Buenos días a todos. Nos da mucho gusto darles la bienvenida en esta magnífica sede, el aula mayor del Colegio Nacional. En esta ocasión tendremos la oportunidad de comentar y discutir varios aspectos relevantes acerca de los temas de investigación desarrollados en la Universidad de Pensilvania. Uno de los objetivos de este simposio es identificar oportunidades de colaboración entre científicos mexicanos y aquellos laborando en la Universidad de Pensilvania. Además, estamos seguros de que este intercambio de información y el hecho de tener con nosotros a los líderes del campo facilitará el intercambio de investigadores y estudiantes mexicanos y aquellos en la Universidad de Pensilvania. En este contexto, me permito sugerir a los colegas y estudiantes aquí presentes que aprovechen los recesos programados para presentarse y platicar con nuestros invitados. El otro objetivo central es conocer, a través de los líderes en el campo, avances de frontera en la ciencia. Hoy tendremos oportunidad de conocer avances recientes en temas como la aplicación de procesos de transferencia electrónica en síntesis orgánica, el diseño de biomoléculas no naturales mediante cálculos teóricos, la conversión de hidrocarburos derivados del petróleo en derivados con valor agregado, el diseño de agentes para la interacción efectiva entre el colágeno y la triple hélice y el desarrollo de ligantes adaptables en función de su estructura y distribución electrónica, además de procesos de transferencia electrónica en solución y en interfaces metálicas. Me acompaña en el presidium el doctor Gary Molander, coorganizador de este simposio y quien es actualmente profesor distinguido y jefe del Departamento de Química en la Universidad de Pensilvania. Queremos principalmente agradecer en este simposio a nuestros colegas y amigos, efectivamente el doctor Gary Molander, quien es profesor distinguido Hirschman McInerney en el Departamento de Química, y su participación estará dividida en dos partes. La primera consistirá en la presentación de la Universidad de Pensilvania y de los programas de investigación en el Departamento de Química, y la segunda se referirá a procesos de transferencia de un electrón en síntesis orgánica. Participará también el doctor Jeffrey Saven, quien es profesor del Departamento de Química. La participación del doctor Saven tiene como título Utilizando la teoría y la computación en el diseño de nuevas biomoléculas y biomateriales. El doctor Daniel Mindiola, profesor presidencial del Departamento de Química, su conferencia tiene como título Haciendo algo mejor que simplemente quemar los hidrocarburos, deshidrogenación catalítica de alcanos volátiles con titanio. El doctor David Chenovet, quien es profesor asistente del Departamento de Química y quien presentará la conferencia intitulada Rediseño racional de la interfase de la triple hélice en el colágeno. El doctor Neil Thompson, profesor asistente en el Departamento de Química, el doctor Thompson presentará la conferencia Evaluando la analogía cúmulo-superficie en ligandos macrocíclicos que son electrónica y geométricamente flexibles. Y el doctor Joe Subotnick, profesor del Departamento de Química, su conferencia lleva como título Transferencia electrónica en solución y en interfaces metálicas, modelos físicos sencillos para reacciones muy complejas. Dear Professors Molander, Saven, Mindiola, Chenovet, Thompson y Subotnick, we appreciate very much your being here at El Colegio Nacional to share with us your experience and knowledge. It is very nice meeting you, and we hope that you will have a good stay in Mexico. Por causas de fuerza mayor no fue posible a la doctora Sara Facaray viajar a México, por lo que no podremos contar con su participación con el tema Procesos dinámicos en vidrios moleculares, que había sido programada a las 4:50 esta tarde. Recorreremos pues el programa de hoy por la tarde y cerraremos este simposio alrededor de las 5 de la tarde en vez de las 6 de la tarde. Escuchemos pues a los expertos que amablemente han aceptado participar en este simposio. Yo estoy particularmente agradecido al profesor Gary Molander por su participación en la organización de este evento. Y estamos seguros de que las presentaciones serán de mucho interés para todos nosotros. Muchas gracias. Empezaremos pues el programa y tengo el gusto de presentar a ustedes al profesor Gary Molander. Trataré de hacer la presentación en inglés, disculpen mi mal inglés. El doctor Gary Molander is Hirschman McEnany Professor and Chair of the Department of Chemistry of the University of Pennsylvania. Professor Molander received his BS, Bachelor in Science, degree in Chemistry from Iowa State University and his PhD from Purdue University. Following a postdoctoral stint at the University of Wisconsin in Madison, he began his independent career as an assistant professor at the University of Colorado in Boulder, rising through the ranks to professor before moving to the University of Pennsylvania. His research interests are in the development of new synthetic methods for organic synthesis, particularly through the invention of transition metal catalyzed protocols for the construction of carbon-carbon bonds. The title of his presentation today is Single Electron Processes Enable Organic Synthesis. Please, Gary.
Thank you very much, Eusebio, for that very kind introduction and for inviting us to Mexico. It's always great to be here with my good friend. I also have to thank Joe Subotnick, who helped coerce my younger colleagues to come and visit. It is a great opportunity for us, and we're looking forward to the day. So, Professor Warisi asked me to present a short outline of the University of Pennsylvania, and I'd like to do that. The University of Pennsylvania, a little bit about Penn chemistry, and also about Philadelphia, where the University of Pennsylvania is located. So this is one of the views of the main campus. The University of Pennsylvania was founded in 1740, so it's one of the earliest universities founded in the United States, and it was founded by a famous statesman, Benjamin Franklin. It's a private Ivy League institution with 4 undergraduate schools. These are arts and sciences, nursing, Wharton, and the School of Engineering. There are also 12 graduate and professional schools. These are things like the medical school, the nursing school, law school, vet school. There are 21,000 students at the University of Pennsylvania, almost evenly divided between undergraduates and graduate students. And it turns out that 17% are from Mexico and Canada, probably about 5 to 7% students from Mexico at this particular time at the University of Pennsylvania. There's 2,500 faculty at the university over all the schools, and those faculty raise over $1 billion in research support. So it's a very intensive research university in the United States. So in the United States, many people like to rank things, and so this magazine, U.S. News and World Report, likes to rank universities on the basis of various factors, and the University of Pennsylvania in 2017 was ranked among the top 10 universities in the United States by whatever criterion this magazine utilizes. And you see we're in very good company with places like Princeton and Harvard and Yale and Columbia. So I think it is a very highly regarded university in the United States. And chemistry also does quite well. So these are rankings from the Shanghai Academic Ranking of World Universities that was done a couple years ago. These are based on impact factor and H indices and things of that nature. And again, University of Pennsylvania in chemistry alone also ranks within the top 10 world universities in terms of our impact in science. The faculty at the University of Pennsylvania, we have 30 faculty. At this point in time, we have about 150 graduate students and about 45 postdoctoral fellows. We have a very good support staff to support the research and teaching enterprise in the department. The faculty are more or less organized along the lines of biological chemistry, inorganic chemistry, organic chemistry, and physical and theoretical chemistry. So these are the areas that we have reasonable strength in. But looking more globally about the types of things that the faculty do, it becomes evident that we have a lot of collaborative efforts in the department with other entities on campus. So we like to think about our research areas as being in theory, and we have an extraordinarily strong group of theoretical chemists. Also a very strong component in synthetic chemistry, very broadly applied over organic and inorganic. With chemical biology, we have a very strong medical school at the University of Pennsylvania, and so there's a lot of interactions with the medical school and the veterinary school. Also strength in biophysical chemistry and in spectroscopy and measurements. These are some of the areas that I think most of us interact with and engage our research in. Energy is a big and upcoming area of support. Materials and nanochemistry and biomedicine. We interact on campus with physics, the engineering school. We have a nano facility at Penn, laboratory for research in the structure of matter, Institute for Medical Engineering, biology department on campus, the School of Medicine. Wistar is an institute that's located on the campus. And we have a lot of interactions with the pharmaceutical industries, which are located around the University of Pennsylvania. So, for example, Merck, Bristol-Myers Squibb, GlaxoSmithKline, and so forth. The scientific infrastructure in the department is quite good. We have 10 high-field NMRs ranging from 300 megahertz to 600 megahertz. We have a very good and strengthening mass spectrometric facility, as well as an X-ray facility with two X-ray diffractometers at this point in time. Both are relatively new. We have a biological chemistry resource center in which there's located a lot of shared instruments for biological research, MALDI-TOF, PrEP HPLC, peptide synthesis, and cell culture facility. We have a scientific glass-blowing facility in the department to make customized equipment. The computational facilities in the department are quite good. And we also have a very special high-throughput experimentation facility that's used mostly by the synthetic chemists to do rapid methods development and optimization of reactions. I might also mention that 2 or 3 years ago, we started a Masters of Chemical Sciences program in the department. And this is a terminal master's degree in the department, and it attracts a lot of foreign students who would like to come to the United States for advanced training and learn English a little bit better. And so I think Professor Wiesty has posted this on a website, and so one can go to this website and look and find out about this Master of Chemical Sciences program. So the city of Philadelphia is a beautiful city. It's in the mid-Atlantic on the east coast of the United States. It's a city of probably 3 million people. This is the City Hall, which is a beautiful building. It's French Second Republic architecture. It's the largest municipal building in the United States. And one can take an elevator all the way to the top and get a nice view of the city. This is the Benjamin Franklin Parkway, and on the Benjamin Franklin Parkway there are many nice museums in the city. The city of Philadelphia is also a very historic city in the United States, so the Declaration of Independence was written in Independence Hall, along with the Articles of Confederation, which is the first government established in the United States, and also the Constitution was written in Independence Hall, so that's a very famous place. At the top of Independence Hall is a bell tower, and there's a famous bell that used to be up there. This is what we call the Liberty Bell. The Liberty Bell has a famous crack in it, so it's not in the tower anymore, it's not ringing anymore, but it's on display. And in the past, this has been carried around the country as a display of the liberties that we enjoy in the United States. There's also, as I mentioned, very beautiful museums in the United States, in Philadelphia. The Barnes Foundation was actually started by a chemist by the name of Albert Barnes, and it's a very beautiful museum. There are over 200 Renoir paintings in the museum. There are Picasso's, Matisse, so he was quite a collector. He became wealthy being a chemist somehow. Not all of us become wealthy, but he was able to establish some wealth and to buy a considerable collection of art. The Rodin Museum is also in Philadelphia. It's the second largest Rodin museum in the world after the famous Rodin Museum in Paris, so it's also a very nice museum to come and visit. The Philadelphia Museum of Art is also a very nice museum. They have a good Impressionist collection. There's a collection on heraldry from the Middle Ages, many other collections that are quite nice to see. And this is the first, this is a waterworks. This is the first public waterworks in the United States that pumped water from the river to the residents of Philadelphia. This is in the days before they pre-treated water, so people just got water directly out of the river from this waterworks. And I want to thank everybody for attending today, and especially to Eusebio for organizing this. I know it's a lot of work, but my colleagues and I really appreciate the opportunity to come and describe some of our science for you today. And if you need any more information, I think the department's easy to find on the web, and so certainly welcome to look at our website, and I'd like to welcome people to come and visit Philadelphia and the university and the Department of Chemistry. So at this point, I'd like to change things a little bit and talk a little bit about some science. And our group has been involved for quite some time in a reaction that's of extraordinary importance to the pharmaceutical, agrochemical, and material science areas, and these are cross-coupling reactions. So among the more famous cross-coupling reactions are Suzuki reactions, and Suzuki reactions are reactions in which one takes an organoboron compound and couples it with an aryl halide under palladium catalysis. And it's estimated that over 60% of the carbon-carbon bonds that are formed in medicinal chemistry research are Suzuki coupling reactions. And normally these coupling reactions are done between two aryl systems, so one phenylboronic acid and one aryl halide. And in order to expand three-dimensional space and explore new chemical space in the pharmaceutical and agrochemical industries, one wants to take a look not only at aryl systems, but at alkyl systems. And these turn out to be problematic. This is a collaboration we had between our group and Merck several years ago, where we tried to take a number of alkyl boron compounds and couple them with aryl halides. And these are under traditional palladium-catalyzed conditions. And the conditions were such that we had to use a strong base, and we heated these in toluene water at 100 degrees overnight to get reactivity. And some of the challenges with this are the isomerization that takes place. So we started with isopropyl trifluoroboroids, and we end up with a 8-to-1 mixture of isopropyl to the N-propyl isomers. And this is a result of a beta hydride elimination and isomerization. And you can see the challenge is even greater with more highly hindered systems like the methyl cyclohexyl system, where we achieve the isolation of this material in 89% yield, but as a mixture of 3 of this isomer and 1 of all the other isomers where this aryl ring has isomerized around the ring. And the reason for this is that boron compounds are not very nucleophilic. And so you're trying to move an alkyl group from boron to palladium through a very high energy of activation process. And so that becomes problematic because these, particularly alkyl groups, secondary and tertiary alkyl groups, are very stable. And so what one does is change the ligand. You can add more and more base to these reactions. You can try to heat them more and more just to get over the energy of activation of this process. And I think we and many others were unsuccessful in doing this reliably under normal conditions. And so at one point in time, one of my students said we were really looking at this the wrong way and we should look at a new way to try to do this reaction. And that was to think of this not as a 2-electron process, but as a series of 1-electron processes. And what we mean by that is when you look at the transmetallation from boron to nickel or some other transition metal, this is net redox neutral at the transition metal. So if we start with nickel 2 or we start with palladium 2 as a catalyst, we end up with nickel 2 or palladium 2 as an intermediate in these reactions. And so the student, John Tellis, thought that really what we should do is think about this as a series of 1-electron processes where we would oxidize this carbon X bond, carbon-boron bond, to generate a radical. That radical could engage with a nickel catalyst, and this would be a net 1-electron oxidation at the nickel. And to achieve the overall transmetallation, all one has to do is reduce this complex, and that would affect the overall transmetallation. And the advantage of this is the fact that these 1-electron processes are typically very low energies of activation. And these processes, the oxidation and the reduction, are knowable by cyclic voltammetry. So you can measure the oxidation potential it requires to oxidize these carbon-boron bonds and the reduction potential it takes to reduce the nickel from nickel 1 to nickel 0. And furthermore, the real transmetallation is a very low energy of activation process. So what is effectively the transmetallation, that is placing an R group from boron under the nickel, was described as barrierless, in fact less than 4 kcals per mole. So what's the issue with this? The real issue to think about is we have to have an oxidant and a reductant in the same flask at the same time. And that seems counterintuitive, but this is where photoredox catalysis comes into play. So there are a series of catalysts early on based on ruthenium or iridium complexes that undergo photoexcitation, in which there's a metal-to-ligand charge transfer making the metal center oxidizing and the ligand array reducing. And so in fact, in this type of complex, we have both an oxidant and a reductant in the same complex at the same time. And this is what facilitates what we call dual metal cross-coupling reaction, single metal transmetallation. The advantage of this is that in a 2-electron process, where we're always trying to lower the energy of activation of the transfer, of the transmetallation, or we're trying to find conditions to get over that energy of activation. Here, by photoexcitation, we gain 45 to 60 kcals per energy in potential energy, and we can generate high energy intermediates using this excited state of the catalyst. And once we generate those high energy intermediates, everything else cascades downhill. So we don't have to worry about high temperatures or any of these other factors that would get us over energies of activation. We're already very high in energy, and we just have to tumble down into the final products. So this is the catalytic cycle, actually 2 cycles that we designed because it's a dual catalyzed process. So in this process, we're going to have a photoredox catalytic cycle and a cross-coupling cycle that are going to merge at one point. So in the photoredox catalytic cycle, we have to photoexcite some photocatalyst to generate a species that can either be an oxidizing or a reducing agent. We typically use this as an oxidizing agent. So we're going to oxidize this carbon Y bond to generate a radical. That radical is going to be fed into the cross-coupling cycle. So in the cycle we designed, we thought that we would have a nickel 0 catalyst that would engage with this, in this case, benzyl radical to generate a nickel 1 species. This nickel 1 species could undergo oxidative addition to generate a nickel 3 complex, and this nickel 3 complex could undergo a known reductive elimination to generate the product we desired and a nickel 1. And now to close both cycles, the cross-coupling cycle and the photoredox cycle, the nickel 1 has to be reduced and the photocatalyst has to be oxidized. Okay, so how do we bring these two cycles together? What we need is to drive both of those cycles thermodynamically. And to do that, we look at the redox potentials of the various reactive intermediates, catalytic intermediates along the pathway. And in the photoredox cycle, the critical thing is that we have to be able to oxidize these trifluoroborates. And we can measure that oxidation by cyclic voltammetry, and we find that the redox potential is minus 1.1 volts. This is just a short table of various catalysts that one can think about using. When we look at this table, we see two complexes that are capable in their photoexcited state of oxidizing the trifluoroborate. One would be this ruthenium BPZ complex. The other one would be this iridium complex. Okay, so either one of these would work to oxidize the trifluoroborate. But in the cross-coupling cycle, we also need to reduce the nickel 1 to a nickel 0 complex, and that has an associated redox potential. And so when we look at the two catalysts that had the oxidation potential to oxidize the trifluoroborate, only one would be thermodynamically favored to be able to reduce the nickel 0. And so we started our chemistry using this iridium complex to see if we could achieve these cross-couplings. As I said, at the University of Pennsylvania, we have a high-throughput experimentation facility, and so we can do these experiments. The students can run 100 or 200 reactions a day on very small scale. And we designed an LED array to shine light into these reactions. So here's the LED array under a reaction block in which there's 96 vials that we can run 96 reactions at once under blue LED light. So that's how we optimize the reactions. And some of the results then I'd like to show for these secondary alkyl couplings. So you remember that we did these in collaboration with Merck. We had to heat these to 105 degrees. We got isomerization. Under photoredox conditions, none of these materials isomerized. We can do these at room temperature just overnight by shining light on the reactions. And so this actually solved a huge problem in cross-coupling of secondary alkyl boron compounds. And the reaction works for a number of different complexes. So for example, cyano groups are often reduced by nickel complexes at high temperatures, but the cyanopyridine, which is very susceptible to decyanation under nickel catalysis, we can tolerate a lot of different functionalities, including having a lot of nitrogens in the molecules, which the pharmaceutical and agrochemical industry really requires to make pharmacologically active drugs. This cross-coupling is much different than traditional two-electron processes. And so we can take, for example, a bromochloropinacholboronate that one could use for palladium-catalyzed reactions and cross-couple that selectively at the bromide under photoredox cross-coupling conditions to form a new carbon-carbon bond and leave this carbon-carbon bond in place. So pinacholboronates are not subject to photoredox conditions because they're tri-coordinate compounds, isoelectronic with carbocations, are not easily oxidized or reduced. So then one can take this material and do a traditional Suzuki under two electron cross-coupling conditions and form a new carbon-carbon bond. One also has a chloride here that one could also do a further cross-coupling reaction or further elaboration. So this leads to very rapid entry into more complicated molecules through a modular type of process. I want to just talk about some of the kind of special types of cross-couplings we've done with some different subunits. We had done this type of cross-coupling under palladium-catalyzed conditions with a beta-trifluoroborado-carbonyl, and that required, again, palladium catalysis at 105 degrees with 5 equivalents of cesium carbonate. We could do amides, which are very stable compounds, but we could not do ketones or esters because under those conditions they reacted with the base. So under photoredox conditions, very mild conditions at room temperature, we can do both alkyl and aryl ketones. We can do esters. We can also tolerate a number of functional groups, including esters, aldehydes, nitriles, free alcohols, and triflates, because bromides cross-couple in the presence of triflates. And again, we can incorporate a lot of nitrogen heterocycles in these, which is very important. This is another very special case. When we did a SciFinder search on this subclass of compounds, we found less than 10 of these materials in the literature. And the reason is because these trifluoromethyl groups are very challenging to put into these diarylomethanes. And one of the reasons is that organometallics with a metal at this carbon are very challenging to make because they undergo rather rapid beta fluoride elimination to generate the difluorostyrenes. But we can make these trifluoroborates very reliably. They're stable compounds. In fact, all the trifluoroborates and all the silicates I'll talk about later are crystalline solids or air-stable materials that we can put in bottles and store for months. So we made these materials, and we can do these cross-couplings quite nicely in a variety of ways. One of the things I'd like to point out is that this dibenzyl bioxazolene ligand is a chiral ligand. We're starting with a mixture of R and S, or a racemic mixture of this trifluoroborate, but you see down here we can engender asymmetry in the final product, so we get a 60% EE without trying to optimize this reaction. So there are two ways to think about how that might happen. One is a stereoselective radical capture, where the energy difference between this prochiral radical and the chiral ligand come together and just snap shut, and there's an energy difference between these two, and then that leads to the final product. The other thing that could transpire is a rapid equilibrium. So there's a radical coming on and off to generate two of these radicals. These would be diastereomeric complexes that may decompose at different rates. And so one of my colleagues at Pennsylvania, Marissa Kozlowski, did the calculation on this. In fact, found that it's actually the latter. We're under Curtin-Hammond regime. If one looks at this diagram, I know it's pretty small from the back, but you end up with a nickel-3 species in which there's a very low energy surface to go from this nickel-3 species to a nickel-2 species where the radical is coming on and off. And so it's actually the rate of the reductive elimination that determines which of these enantiomers is made. And one can take advantage of that by designing chiral ligands on these nickel species to induce asymmetry in these types of cross-coupling reactions. So one can start with racemic boron compounds and end up with enantiomerically enriched products in the end. So just some other types of subclasses of cross-couplings we've done. These amino acid derivatives work very nicely, and you can see the diversity of halides that we can use. We can start with a coumarin derivative, SF5 derivatives, sulfonamides work quite nicely. All of these, there's complete stereochemical fidelity. The conditions are very mild, so we don't lose any of the enantioselectivity in these amino acids. We can use bromocaffeine with a lot of nitrogens, oxidiazoles, and boronic acids. The yield's a little bit lower here because boronic acids are very challenging to isolate in pure form. This is also a very unusual cross-coupling reaction. I think when most people look at this product and think you want to form this carbon-carbon bond, what you might think about is doing a simple Grignard addition to an aldehyde to form that bond and the alcohol. But what we're doing is reversing the reactivity of these species, and we're using this as a nucleophilic reagent and an electrophilic aryl or heteroaryl bromide to generate these types of alcohols directly. And the advantage of this is that there are tens of thousands of aryl and heteroaryl bromides. So if one thinks about structural diversity and generating libraries of compounds, it's much easier to do this type of compound from these stable starting materials and react them with 10,000 stable heteroaryl bromides than it is to try to do 10,000 reactions with Grignard reagents. And again, we can tolerate a lot of different functional groups that one could not tolerate with the Grignard reagents, such as aldehydes, nitriles, ketones, halides, sulfonamides, and even boronate esters. We've used this inverse reactivity as well for chrominone synthesis. So chrominones are important in agrochemical and pharmaceutical industry. And we've done this under conditions where we use an organic photoredox catalyst. So this is an organic photoredox catalyst. So in this transformation where, again, this is the nucleophilic carbon, and we're reacting this with a variety of electrophiles, we only have the only metal in this reaction is 5% of a base metal catalyst, the nickel chloride, otherwise completely metal-free. So it's a much more sustainable and green approach to organic synthesis of these types of materials. This is a very challenging reaction that we've recently started to establish. So as far as I know, no one has ever done a tertiary alkyl coupling in Suzuki-type condition with boron reagents. And we're able to do that with trifluoroborates under this set of conditions that were optimized through high-throughput experimentation. There are some limitations to these reactions. We do have to have electron withdrawing groups on the aromatic ring, but you see we can tolerate different functional groups, esters, and ketones in this type of cross-coupling. So at least it gives us a start to look at tertiary alkyl cross-coupling, and we've done this with bicyclic systems such as adamantyl trifluoroborate as well. So we've looked at a number of different platforms, a boron compound, and we're starting to look at different platforms for the electrophile. So typically Suzuki coupling reactions are done with aryl halides or heteroaryl halides. Now we're starting to look at other electrophiles. We've done acid chlorides, cross-coupling to generate ketones. Acid chlorides are challenging to handle because they're very hydrolytically unstable. So we turn to amides, which are really stable compounds that can be carried through several steps. And we found conditions whereby we can cross-couple these amides with a variety of different ketones or trifluoroborates to generate these ketones with secondary alkyl systems, with alpha-amino trifluoroborates, alpha-alkoxy trifluoroborates, and the beta trifluoroborato carbonyl compounds work very well. What we're most excited about, though, is taking carboxylic acids directly to ketones. So this is one of those fundamental reactions that you think should be known, but in fact is extraordinarily difficult to carry out. How do you generate a ketone directly from a carboxylic acid? And there are really no good ways to use this for complex molecule synthesis. You can use reagents like methyllithium or butyllithium, which are very harsh reagents that don't tolerate any functional groups. But if you want to do this with functionally complex molecules, there is really no way. And so we found a way to do this by in situ activation of the carboxylic acids. So we use dimethyl dicarbonate. We mix the carboxylic acid, dimethyl dicarbonate, and the trifluoroborate all together. We generate a carbonic anhydride intermediate that engages with the trifluoroborate under photoredox conditions to generate these ketones directly. So this is just a fundamentally new type of reaction that allows us to do these type of cross-coupling reactions with dense functional groups, such as those found in amino acids. We can have a free NH on an indole. You can have a free hydroxyl group. You can have all kinds of halides, perfluorinated compounds, triketones in complex molecule synthesis, esters, lactams, and so forth. So we think this is a new approach to ketones that fills a really large gap in terms of synthetic organic chemists' access to very simple types of compounds. The scope, again, is quite good. We can use a number of different trifluoroborates. So again, secondary alkyl systems, alpha-amino systems, alpha-alkoxy systems, azirodenyl systems, and so they all, again, seem to work quite nicely and is broadly adaptable. Other electrophiles we're taking a look at are vinyl epoxides. So vinyl epoxides can be ring opened with cuprates or Grignard reagents, but both are derived from very reactive intermediates and so have their limitations. And again, with the trifluoroborate, we can put functional groups in the molecules. So an alpha-alkoxy group with an ester can work quite nicely in these types of nucleophile electrophile reactions as well. And we've also looked at different nucleophilic precursors to the radicals. So trifluoroborates are great, but we also wanted to look at some other precursors to the radicals, and the silicates came up. These are more soluble than the trifluoroborates. These salts are more soluble in most organic solvents. They also have a lower reduction potential. So with the trifluoroborates, we were not able to do primary coupling reactions because the oxidation potential was too high. So with the silicates, we're able to do primary alkyl coupling, even in polyfluorinated systems that have an oxidation potential that's even higher. And really, for the first time, we're able to introduce primary amines without protection late stage in cross-coupling reactions. So as far as we're aware, no one had ever put amines, unprotected amines, into molecules late stage through cross-coupling. And so that's another advantage of being able to use the silicate cross-coupling and single molecule or single electron transmetallation processes. Again, it's a mild procedure, so we can tolerate boronate esters in these molecules, and you can see how you can build up molecular complexity quite rapidly, because you can always do cross-couplings or other transformations with the pinnacle boronates once these are included in these molecules with a lot of different functional groups, from amines, amides, urea derivatives, and so forth. We've looked at cross-couplings with these borazines. We have a program in borazine chemistry. Borazines are isosteres of aromatic systems. So if you imagine the electron pair on nitrogen bonding, overlapping with the empty p orbital on boron, this is isoelectronic to a carbon-carbon double bond. And so this unit is isosteric and isoelectronic to a naphthalene system. And these are beautiful substrates for cross-coupling reactions. They work typically in greater than 90% yield. And these materials are now being used in the pharmaceutical industry, again, to explore new chemical space for development of drugs. And these compounds have never been made before in this way. And again, one can incorporate primary amine into these compounds quite easily. One can also incorporate the halide on a aryl group off of the boron. They don't have to be in the borazine ring. And these also work quite nicely in a number of different systems with a lot of unprotected functionality to generate these types of elaborated systems. We've done alkenyl halide cross-coupling reactions with the silicates. For reasons we don't really understand, we were unable to do that with the trifluoroboroids, so that allows us entry into this class of molecules. These reactions, again, are totally stereospecific, so we started with a Z or cis alkene, alkenyl halide. We end up with a cis alkene as a final product, and again, a lot of different functionality can be incorporated into these molecules. We're cross-coupling now isocyanates, so isocyanates obviously react with Grignard reagents, but Grignard reagents don't tolerate a lot of functionality. So you're limited in terms of the molecular complexity one can have. But with silicates, we're able to do this addition to an isocyanate. This is a nickel-promoted reaction. It's not a straightforward radical addition, but is nickel-promoted. And again, a wide range of functional groups can be incorporated into this particular protocol. Lots of different silicates can be utilized. So you can have cyano groups, polyfluorinated systems, esters, indoles, and urea amides can be incorporated as well as a parole. So finally, the last type of reaction I'd like to talk about is a thioether synthesis. And this came about as completely as accidental. The postdoc Mathieu Geoffroy, who was doing this chemistry, was taking this thiol-substituted silicate and doing a cross-coupling reaction. And we thought we would form a carbon-carbon bond, but what happened is we ended up forming, as you can see, a carbon-sulfur bond. And so what happens is the carbon-silicon bond is cleaved, and we generate a radical. But that radical undergoes a very rapid hydrogen atom abstraction from the thiol to generate a thiol radical. And the thiol radical interacts with the nickel, and then oxidative addition occurs, reductive elimination, so we end up with a carbon-sulfur bond instead of a carbon-nickel bond. And this is a very nice protocol for the synthesis of alkyl aryl ethers, and completely complementary to the other types of thioether formation that's used, SNAR reactions or SN2 type reactions. And if we're not using thioether attached to the silicate, then we can use a sacrificial silicate to generate a radical that will abstract the hydrogen, and then we can connect any two pieces, an aryl or heteroaryl halide and any thiol together to generate these thioethers. And so it's a unique approach to making these materials. And we're taking advantage of that in making some biomolecules that are heavily functionalized. And we started off slowly with just some peptides like tiopronin. And so in tiopronin, we have an amide bond. We have the thiol, obviously, from cysteine. And we also have carboxylic acid that's free. And we could connect this to a number of different aryl and heteroaryl halides, including one with a nucleic acid base. So extensive toleration of a lot of different reactive functional groups in these molecules. We've moved up now to do glutathione, and so now we have 2 free carboxylic acids, a free amine, and the thiol from the cysteine. And again, this reaction works incredibly well. These are isolated yields of these materials, selectively reacting at the thiol. And what we've been able to do is to move this up into even further, more complex molecules with a lot of different functional groups. So for example, coenzyme A has a nucleic acid portion with a phosphate, free OH, an amide, and the thiol. We get 90% conversion with making the thioether exclusively at the SH residue. And we also, in collaboration with James Peterson's group, used a polypeptide. And you can see all kinds of functional groups, indoles, histidines, carboxylic acids, phenol derivatives, a coumarin that can be used as a dye in these materials, 80% conversion to the S-thioether compound. So these are some of the things that we've been able to accomplish through this novel concept of dual metal catalyzed photoredox, transition metal catalyzed reactions in which we take advantage of single electron processes to overcome energy barriers that are too high in the dual electron process. And so, like everyone, we have to thank friends, and we have a lot of friends in the U.S. that supports the research. So the NIH, NSF, a lot of different companies, pharmaceutical companies in particular, have supported the research in this area. Most of all, I need to thank an incredibly talented and hardworking group of students that carry out the work and contribute enormous capabilities, both intellectually and, of course, in the laboratory. So I need to thank them, and again, thank Eusebio again for inviting us, and thank you for your attention this morning.
Questions? Y si tienen alguna pregunta. Por favor.
Thank you, Professor Molander, for the wonderful talk. I have enjoyed it very much. You have talked about a collaboration with Merck, maybe in this photoredox reaction. I'm wondering if you see this kind of reactions applied in ton scale. I mean, the photoredox technique, or it's only for the screening?
So what I can tell you, first, we don't have a collaboration with Merck in photoredox chemistry. We had a collaboration on this setup of the high throughput screening facility. So the way to do large scale is to do photo flow. So you have a flow system, and I know that Merck has set up a photo flow system. I know that Novartis has a photo flow system. I know that Vertex has a photo flow system. I don't know about tons, but certainly they're making hundreds of grams. And the reactions that we do, they're done in anywhere from 3 hours to 24 hours, I would say. And the reason for that is solely due to photon flux. When you shine a light in a flask or a vial with liquid in it, you're only getting light through the first fraction of a millimeter of the flask. So if you can get photon flux through the reaction, then they go in. Most of these reactions that I've talked about, we know from information we receive from Vertex and other places, they go in 15 minutes to 30 minutes. So it's not a problem of the length of time or anything, it's how much throughput you can do, and that has to be done in flow.
¿Alguna otra pregunta o comentario? Si no, agradezcamos al profesor Molander por su interesante presentación. Tengo ahora el gusto de presentarles al profesor Jeffrey Saven. Professor Jeffrey Saven earned a bachelor's degree in chemistry from the New College of Florida and a PhD in chemical physics from Columbia University in New York. After a U.S. National Science Foundation postdoctoral fellowship at the University of Illinois at Urbana-Champaign, he joined the faculty in the Department of Chemistry at the University of Pennsylvania. In addition, Professor Saven is associated with the Penn's Laboratory for Research on the Structure of Matter, the Genomics and Computational Biology program, and the Biophysics and Biochemistry program. Within Penn's Undergraduate College of Arts and Sciences, he co-directs the Biochemistry program and the Roy and Diana Bagelos Scholars Program in the molecular life sciences. Research interests in the Saven group include molecular simulations and modeling, the computational design and redesign of proteins and other molecular systems, as well as protein and polymer folding. Today, his presentation has as title, Using Theory and Computation to Design New Biomolecules and Biomaterials. Please, Professor Saven.
Okay, thank you very much. Good morning and buenos dias. Thank you to all the staff and Professor Oresti here at El Colegio Nacional, and also to the groups at Penn that helped make this happen. So what I'll talk about today is examples largely of how we can use theory and modeling and calculations and simulation to understand and to redesign large molecules. I won't talk so much about the theory, but I'll try to give an idea about how the theory works. So certainly we all know that DNA encodes for proteins, right? And DNA is largely a one-dimensional sequence of the nucleic acids, which codes for a one-dimensional sequence of the amino acids. So that means you have very complex structures that are encoded in polymeric molecules. And what's key to controlling the structure and function of the molecules is controlling the sequence. So we have very good methods for dealing with DNA and controlling its sequence and synthesizing it in large quantity, of replicating it, of expressing it, or in the case in eukaryotic organisms or in prokaryotic organisms, to make quantities of proteins. That's oftentimes a stumbling block with regard to studying natural proteins. What's kind of more problematic is how do we encode a particular protein and protein structure and protein function into a particular sequence of amino acids. And that's a large sort of area of research that my group is involved in. So we know that proteins we can describe in many sort of classes of structure in terms of the individual sequence of the amino acids, what type of local structures those form, or secondary structures. And those can come together to form structures that are contained within a single chain, tertiary structures, and multiple chains or multiple protein molecules can self-assemble into quaternary or even higher order structures. So somehow we can encode very complex structures into sequences of the amino acids. And we know that we're able to tabulate and determine the structures of many different types of proteins. So here's just a rendering of a poster from the Protein Structural Data Bank in the United States, contained at this website. And we see, up here we have very tiny molecules like water and glucose and adenosine triphosphate, or ATP. And then we can see that we get a wide variety of different types of structures that we can form with proteins. Later on today, we'll hear a great talk about collagen and how we can engineer and re-engineer collagen. But we can see we get proteins that are sort of enzymatic, proteins that reside within membranes. I'll talk about that later today. And also proteins that associate into higher order assemblies. So what we're able to work with and what we have on hand are nature's proteins or nature's molecules, but it sort of suggests that if we can control sequence at the level of DNA or sequence at the level of amino acids, which we can do now using genetic and synthetic methods, a key stumbling block is deciding what sequence to choose. And so that's what I'm going to talk about today. So my group does largely, as was mentioned in the introduction, computational studies of molecules, how we might simulate them, how we might understand them, usually larger molecules like proteins and polymers. But also, we've developed a set of methods to use with which we can understand how to engineer or re-engineer proteins or how to build them from scratch. So one example I'll talk about is how we might design a particular protein crystal. And then the other example sort of project or set of projects that we have, so I'll talk something about how we might make or engineer variants of membrane proteins, a notoriously hard class of proteins to work with, and how we might make water-soluble variants that retain many of the same properties that the membrane-soluble form does. All right. So with regard to protein crystals, certainly protein crystals and crystallography has a long history. Crystallography is perhaps the most high-resolution method we currently have to determine the structures of molecules, and that certainly applies to proteins as well. So there's a tremendous amount of effort with regard to understanding the crystallization process, and also understanding how we would get high-quality crystals. This is oftentimes the fundamental stumbling block, the impediment with regard to getting structures or high-quality structures of proteins. How do we get high-quality crystals? So certainly, protein crystallization has a large number of applications with regard to understanding the structures of biological molecules or structural biology. All right? But we can also think about these crystals as materials. That if we could get control over these materials, right, we can engineer sort of arbitrary sequences of very large molecules, and that those molecules have surfaces, and those surfaces we can think about engineering so that they will self-assemble into a complementary fashion. Right, so we can think about building things that are structured on many length scales, from the atomic length scale up to length scales on the order of millimeters or beyond. Can we use these as scaffolds or templates with regard to positioning things? Certainly that's one thing that biology does. Uses proteins to template the formation of and precipitation of certain types of oxides, for example, in the formation of shells and nacres. And also, can we begin to think about hybrid materials that involve both hard and soft components? Hard in terms of oxides and metals, soft in terms of proteins. So, but one thing when we do protein crystallography with natural proteins is that we usually don't have control over the particular crystalline form that results. Usually what the protein chemist does is that he or she will isolate a particular protein and then expose it to a wide variety of conditions, hope that that will crystallize, and that it will crystallize and yield crystals that are of high enough quality that we can do diffraction studies to just study the structure of that one protein, that one building block. Right? But what we wanted to see if we could do is, could we get control over the overall structure, the symmetry, the space group that the protein forms? And so we can start with a particular building block and then engineer the exterior surface so that it comes together and self-assembles into now a predetermined symmetry or space group. Right? And this is a collaborative group involving several different groups, particularly that of Bill DeGrotto and some great graduate students at the University of Pennsylvania. All right, so one thing we need a structure or building block. So in that respect, we're going to choose a small or relatively simple or easy to work with protein, just a homotrimeric bundle of peptides. So 3 equivalent peptides come together to form a folded unit. And then we'll look at engineering the exterior of that folded unit so that it will self-assemble into this preformed crystalline lattice. All right, so there's 2 sort of complementary effects that go into play. We have to pick a structure, that's the structure of the building block, and a structure of the overall lattice. So that's something we can do a priori. And then another thing we need to do is need to determine, well, what is the sequence of the amino acids that we're going to choose for these peptides that self-assemble, both to form the individual building block and to form this larger scale assembly. All right? So all of these are now potentially at the control of the researcher, but we can carefully choose both structures and sequences of the amino acids. So with regard to our building block for the crystal, we're going to choose something very simple. It's going to be easy to generate and easy to work with. It's going to be something 3-fold symmetric. This is what's referred to as a parallel 3-helix bundle or parallel trimer. And we'll take advantage of that helical periodicity. For each helix is on the order of 26 amino acids. I guess that's not indicated here. We're going to have a hydrophobic core that holds the 3 helices together in aqueous media at sufficiently high concentrations. A motif like that can be generated computationally or identified by just modeling helical structures, and that's also been explored in a study in the late 1990s from the Eisenberg and the DeGrotto groups. And so once we've done that, that leaves 18 exterior positions with which we have to choose any one of potentially the 20 different amino acids. So it turns out we're going to eliminate some. We're only going to allow 18 different amino acids at each of these 18 positions. That means that, in principle, we have 18 to the 18th possible sequences. So that's somewhat problematic. So we're going to use and develop computational methods that allow us to sort of not directly address every single member of that ensemble, but to say something about what amino acids are likely to be appropriate. So then we pick a particular crystalline space group for our lattice. So we're going to choose one that's called the P6 space group. The 6 comes from the 6-fold symmetric axes contained within this space group. So you can see sort of a honeycomb type structure with regard to this lattice if we look at one perspective. It's a layered structure in that we have one layer and then we just translate up one direction. So there's no shift, there's no screw axes or anything like that. We just have layers stacked all on top of each other. And I've colored them to indicate that all these layers, in each case, the peptides are all oriented parallel to each other. And we choose this for a variety of reasons. It's one of the highest symmetry space groups that's known for proteins and peptides. High symmetry space groups are advantageous for several reasons. They make, to some degree, they make calculations easier, but they also make structure determination easier as well. Oftentimes the diffractograms or the diffraction patterns are easier to interpret. There's higher signal to noise. That this particular space group is not so common among naturally occurring protein sequences. There are some that are much more common, but it'd be sort of more convincing if we could coerce proteins or coax, maybe coerce is too strong a term, to form a particular crystalline space group that's not so common. It's going to have large tubular channels in the order of sort of a nanometer or 2 nanometers across and so we can think about then potentially using that as a way to get things inside and outside of the crystal. We have this polar ordering that's not so common among crystals in general that I mentioned before. And what we're going to focus on is using largely non-covalent, non-coordinating protein-protein contacts to form these types of assemblies. So there's been a wide variety of different types of studies where people have engineered peptides and proteins. Oftentimes they'll put reactive groups or they'll put metal coordinating groups on the exterior of the protein and use those as points of attachment or points of contact between neighboring proteins. So we're not going to do that. We're going to try to engineer things in a way that's comparable to what's usually done with regular protein crystallography. So now, the computational component, with regard to building those lattices, that's very straightforward computationally, right? We can just leverage the structures of those individual helical peptides, make the trimer. We can build the trimer and its nearest neighbors in the context of the lattice, and we can continue to build out the lattice from there. Right, so this can all be computationally. In fact, what we can do is we can leverage the symmetry, the periodicity of the system, and apply a form of periodic boundary conditions to facilitate both the modeling and the calculations. So that gives us a way to generate many different possible candidate crystalline structures. I could imagine changing both, for example, what the distance is between nearest neighbors, or there are other sort of symmetry transformations I can do that are consistent with that particular lattice. So we have ways to generate lots of different crystalline lattices that are consistent with this P6 space group. We don't necessarily know which one is best to start with, and so now we need a method to basically determine what types of sequences are consistent with a particular lattice. And so my group has worked on developing a methodology for doing that. There are other groups that do related things. In our approach, basically we start with a particular protein structure. So this is a natural protein, a natural protein domain, the SH3 domain. We want to try to figure out what types of amino acids are allowed within the context of that particular structure. And the types of outputs that our calculations provide is at each variable position, for example, this position 13, whose wild type is this N residue or asparagine, right? How likely are each of the amino acids at each of those variable positions? Right? So what we'd like to do is be able to do that not necessarily totally derived from nature, because we'd like to be able to sort of go beyond naturally occurring proteins. So we're going to use inputs that leverage a lot of what's known or been parameterized for proteins and peptides, in particular potential energy functions or force fields that are commonly used to simulate and understand proteins. Right? So we start with a particular target structure. We have energy functions or force fields or potential energy functions that quantify, from a physical chemical standpoint, interactions that the amino acids have with each other, that they have with the backbone structure, that they have with any other molecular species that might be present in this protein. Right? And then we also want to be able to impose constraints on the sequences. We want to make sure that they're compatible with this particular structure. I might want to pre-pattern things so that I only have hydrophobic residues in a certain region, hydrophilic in another. And I might want to have some functionality built into the protein. For example, a metal coordinating site or a substrate coordinating site. So within this methodology, we can input all of this. And what comes out of this is basically site-specific probabilities of the amino acids at each variable position. So sort of this physical chemically guided characterization of the ensemble of possible sequences that are consistent with a particular structure. And then we can apply this to relatively large proteins on the order of hundreds of amino acids, We can include this to guide both the realization of specific sequences, potentially even whole ensembles of sequences. And then if we build this upon basically sort of physically derived potential functions, then we can think about applying this to non-biological systems as well. Okay, so I'm going to skip over a lot of the details of the theoretical development, but I just want to say that in principle, what it derives a lot from is sort of core ideas from statistical thermodynamics and from sort of physics and chemistry in general, particularly that applied to many body systems and to condensed matter systems. So and basically, if we look at sort of thermodynamics, one thing we know that is if there's some probabilistic like quantity, something like a density, all right, and we want to determine what that property is at equilibrium, oftentimes there are rules or principles from statistical thermodynamics that guide that. We know that if there are at equilibrium, is anything that can move around, whether that's a wall inside some box or whether that's a probability distribution, that will readjust so as to optimize, in this case, an entropy at equilibrium. I could choose other external macroscopic constraints, and the system would then seek to minimize an analog of a free energy at equilibrium. But that idea, that concept, that now I have essentially a variational principle, that I can look at something, for example, what the density is throughout this whole box, at each little region in the volume or each little voxel, what that would be. I have a way to determine sort of what the optimal set of those that are consistent with a particular set of external constraints. So that notion, right, of entropy optimization subject to constraints, we can think about applying to the sequence ensemble problem. There are a lot of analogs. I can talk about basically things that are fixed, like what the overall structure is. I can talk about quantifying energies, for example, interactions that the residues have with each other. And I can talk about things that can move around or vary, all right? And that would be, for example, the likelihood of a particular amino acid in a certain state at a certain site, where that state will be determined by its local conformation and its identity. What particular amino acid or what particular side chain functional group is present at that particular position. So then we can use a similar type of methodology, right? Can we write an effective entropy object and then impose constraints, optimize that to determine what the likelihoods of the amino acids are at each variable position, all right? So since we have this analog that looks like statistical thermodynamics, also like concepts or ideas from information theory, then we're going to have objects that look like those that we get from thermodynamics, like effective temperatures, effective internal energies, effective entropies. It's important to note that here entropy quantifies somehow the number of distinct configurations of the system. Those configurations are specified by the sequence and the sidechain conformations. Right? And so we apply a few extra approximations associated with this type of approach. We develop what amounts to essentially a self-consistent field method based upon entropy optimization. So self-consistent field methods are very powerful, oftentimes widely applied with regard to the structure, the electronic structures of molecules, but also the structures of condensed matter systems like magnets and things like that. And so we can develop an analog of that we can apply now to this sequence ensemble problem for a particular protein. And one key object that we're going to use to characterize sort of ensembles of sequences is the analog of the internal energy, what will amount to an average energy over sequences that take on a particular structure. Okay, so everything is treated atomistically. We use atomistic representations of the amino acids to quantify their energetic interactions, for example, forms of the amber and charm molecular mechanics force field. We have a way to parameterize hydrophobic effects that's relatively crude. So in a calculation like this, where we consider wide-scale variation of the sequence, there's no way we can really treat water atomistically. So we develop other ways to treat basically the solvation effects associated with different amino acids. That's parameterized upon a database of known protein structures. With each amino acid, we allow multiple sidechain conformations, although we discretize those. So we allow a set or a discrete set of conformations associated with each sidechain, so-called rotamer states. And then we're going to go ahead and solve for the likelihood we have a particular amino acid in a certain conformation at a certain site in the structure. And then from that, we can get the likelihoods of the amino acids themselves. Okay, so that's the approach. That's the theoretical approach. Basically, it involves developing a methodology that involves a large number of nonlinear coupled equations that have to do with the interaction of each amino acid with this local environment of other amino acids. And then we solve self-consistently for these likelihoods of the amino acids. So coming back to our crystallization or crystal design problem, I mentioned before that basically we can generate many possible crystalline structures We can do that by just making transformations that are consistent with our P6 space group. Here we look at several of those. So one, we can rotate them within the space group. We can also change the spacing of nearest neighbors, and we can change the spacing between the layers. So in our choice, what we're going to do is we're going to choose this spacing between the layers so that the proteins are poised to hydrogen bond to each other. It's as though it was a contiguous alpha helix, right? So they're going to be very close to each other in this C dimension of the unit cell. And then we're going to look at variation of both this rotation and this distance, which we'll label by R, just how far apart nearest neighbors are in angstroms, and theta, a rotation relative to some initial angle of two nearest neighbors. So we don't necessarily know what is the best point of, what is the best sort of values of these two quantities, R and theta. So we do a scan, right? We build essentially a landscape, or an energy landscape of different possible crystalline structures. So that's what's represented on this energy landscape. So if we go up this scale, that's just the rotation between nearest neighbors, this angle theta. And this one is just the distance between the centers of two helical bundles. As we basically, if we get too close, backbone atoms begin to overlap in space. We begin to explore configurations that are just not physically realizable, right? They're just too high in energy. And that's what this white region corresponds to. And then we move too far apart, the individual amino acids have no contact, have no interaction with each other. And so we see that we go up on this renormalized energy scale. But if we look for deep blue regions or lakes in this energy landscape, we can drill down on those. We can look at the probabilities of the individual amino acids. From that, we can determine an individual sequence, and then we can select that for synthesis and further characterization. So that's what we did with these 5 black dots, right? And so in this case, these two didn't really crystallize. This one crystallized, but at least didn't diffract very well. And this one crystallized, but it crystallized in a different space group, so that the sequence corresponds to this well. Right? And this was all done in-house, using standard sort of situations where we would synthetically, using a peptide synthesizer, make the sequences, purify them, expose to usual sort of crystal screening conditions. And then in most cases, like in these 3 down here, crystals would form in the matter of hours, just having it sit at the benchtop. And then we'd allow the crystals to mature for a few days, and then do diffraction studies just using an in-house diffractometer. So no super high flux or synchrotron resources or anything like that. And that leaves this one here, this piece. Oh, I should mention that this one, I think I mentioned that this one crystallized but didn't diffract very well, but this one did crystallize, right? It did diffract well enough that would actually determine a structure. So what the methodology provides is a way to survey a landscape of different possibilities and then drill down and identify regions that are likely to be promising targets, including regions that can be very far apart with regard to the structure, in this case, the crystalline structure of the assembly. All right, so we get a crystal that's, relatively small, but plenty big enough to do diffraction studies with. I'll skip over how we do diffraction, standard methodology, all right? But here's the model structure that was input to the calculations to determine the sequence, and here's the electron density map that results from the crystallographic studies. All right, so it's a structure whose resolution is plenty good enough that we can determine the orientations of side chains. Just if we look at the spacing between the centers of nearby proteins, we can see that those match up pretty well. We can superimpose 4 nearest neighbors, both in the model and the crystal structure. We can see that those superimpose. We see that there's a very close contact that involves glycine residues, the smallest amino acid, and that's what's rendered via these spheres. And so we have a motif that involves a glycine, a turn of the helix, and another glycine. So this so-called G-XXXG motif that's been widely observed among helix-helix contacts in natural proteins. And here it's just sort of fell out of the calculations for that particular region in the energy surface. Right. We can also superimpose the model and the crystallographic structure. And one thing we see that's not so common among naturally occurring proteins is that we have a string of complementary electrostatic interactions that helps hold the crystalline interface together within one layer. So these types of interactions are less common among natural proteins. They're often thought to be high entropy destabilizing interactions. Then many times protein crystallographers or protein chemists will seek to do mutations to remove residues like lysine and glutamic acid from these types of interfaces. But what it shows is that if we're careful about it and how we select and choose them, we can come up with basically a coordinated set of complementary interactions that helps hold a particular assembly together. Okay, so the next step is to think about moving beyond that, right? Begin to address, other types of crystalline structures, and also, do we need to be careful about the building block? All right? Can we just, by changing the exterior sequence, can we come up with different types of assemblies? So this is a collaboration with a group at the University of Delaware and also groups at the University of Pennsylvania. One key collaborator or one key student involved in the project, all right, is Jose Villegas. Jose, all right, turns out has dual Mexican-American heritage. In fact, he's from San Felipe, which I'm told is the home of the fish taco. At least that's what Jose tells me. All right. And so he came for his graduate studies a few years ago. He should be finishing up in the next year and plans to go on and do a postdoctoral fellowship at the Weizmann Institute in Israel. So here the notion was to pick a particular building block, all right, and then we can imagine looking at that in two different ways. And then we can think about now taking that same building block, that same helical assembly, and putting it in different types of local types of crystalline assemblies or crystalline structures. And so some of those may have six-fold symmetry, some may have four-fold symmetry, some may have two-fold symmetry so locally in the structure. And the notion here is to pick a particularly robust building block so that we can look at wide-scale variation or basically tuning of the exterior sequence by careful calculation so as to get sequences that would now assemble into each one of these different types of structures. All right, so that's what's shown here. So we did calculations. What's a little bit tricky to see, but is that we have these multicolored helical bundles. What you can see is that at least the patterning of the colors is distinct or different in each case. And that's because the exterior sequences were determined in the context of that particular local assembly. So we did scanning through, like we talked about before, we have crystalline parameters associated with each of these assemblies. We can scan through basically the parameters that determine the helical cell properties, or the unit cell properties, and then identify minima in that landscape, and then identify a sequence. And now the next step is to synthesize an individual peptide and see if we can take a single peptide, which will self-assemble to form a 4-helix bundle, and then further undergo coordinated assembly in these three cases, or simply just remain soluble in solution in this case. And so then that could be further characterized in this case with just CD spectroscopy. So this particular sequence that I talked about before, all right, that this one is, at least under the same conditions that we look at these other ones, was not observed to undergo any further or higher order assembly. But if we look in the other cases, which we characterize usually in this case using transmission electron microscopy and small angle X-ray scattering, we can see that in each case we get very different local assemblies. It's a little bit distinct, hard to see, but we have something that's sort of 6-fold symmetric here, something that's clearly 4-fold symmetric here, and something that has a sort of a 2-fold symmetry on this side. And we can show that these are relatively robust. We can go up to very high temperatures. We can change look at assembly over a wide range of different types of conditions. All right. So, and then the second sort of project that I want to allude to or talk about a little bit is how we can develop water-soluble variants of membrane proteins. Membrane proteins are a really important class of proteins, all right, that they're a large fraction of the genome. A large fraction of drug targets, small molecule drug targets, are integral membrane proteins, those that span the lipid bilayer. They're typically very hard to work with, so it's sort of a heroic thing to determine the structures of integral membrane proteins. They typically, they don't express very well, either, particularly if you take it to some other organism to express the protein. They have relatively low solubility, as you might imagine. They have many hydrophobic residues on the exterior of the protein, so they're typically very aggregation prone, hard to work with. And if we just look at natural abundances, there's just not that much of them. We don't need much of a membrane protein to fulfill the functionalities that the cell requires. In part because they reside in this sort of two-dimensional layer. In another part, many of the responses that we get from membrane proteins are amplified. They're key cell signaling events, so we don't need that many. Typically what's done with membrane proteins is that they are dispersed or somehow solubilized or somehow spread out so that we can do binding studies or biophysical studies or determine the structures of these proteins. All right, so just going back to our thing for the PDB, we can see that there are several membrane proteins that span the lipid bilayer. Right? So we're going to focus, can we think about how we can make these proteins easier to work with and easier to study? Right? So basically, can you take a membrane protein and then develop a variant that still maintains a lot of the properties of the membrane-soluble form, but that is now a water-soluble protein? Right, so why would we want to do this? One is that usually it's much easier to get soluble proteins in large quantities, and that's perhaps one of the most important reasons for doing this. So if we wanted to do biophysical studies, or if we wanted to somehow repurpose an integral membrane protein for some other function or activity, right, that'd be much easier to get large quantities of the protein if we could express it as a soluble form. Facilitates structural studies. Water-soluble proteins are much easier to work with than membrane-soluble forms. Functional studies, if we want to look at binding of agonists, antagonists, ligands, inhibitors, drug targets, those types of studies are usually much easier with water-soluble forms. And just biophysical studies. You know, what role does the membrane play determining the structure of the protein, or can I determine that largely in the context of proteins or interactions that are consistent within a particular structure? And then lastly, we can think about repurposing membrane proteins, which are key recognition elements of cells, how cells interact with their local environment, how they pick up and recognize chemical signals, how they interact with drugs, how they interact with signaling molecules. All right? If we can do that, we can think about repurposing membrane proteins for other types of applications. So one target we chose to start with was an ion channel, a potassium ion channel, this integral membrane protein KCSA. You make a few mutations to this, and now it will bind a toxin. So many snake and arthropod and insect toxins act by binding to ion channels. All right, so that's the case of this agitoxin 2, a toxin derived from scorpions. All right, so now we have a functional assay, at least to determine if we make any sort of variant to this protein, is this domain correctly presented? All right. And so in this case, we had a structure of the KCSA to start with, a crystallographic structure. Right? And so then we could identify the exposed hydrophobic residues to mutate. And then we would apply the calculations. The calculations provide what types of amino acids are positioned on the exterior positions such that they're consistent with each other and consistent with being exposed to solvent. Right? And once we've done that, now we've identified a new protein sequence. A gene can be ordered or built that corresponds to that sequence. We can express that gene. Now, this protein we can express in E. coli, perhaps the standard expression system, and it comes out in the soluble fraction, so it's easy to isolate and easy to work with. We made a few, it turns out the initial construct was a little bit aggregation prone, so we made one or two extra mutations, and we got one that was largely the tetrameric, tetrameric form in solution. And then, so we could go through, I'll just summarize what the findings were. This came out a while ago. Basically, we could summarize, or what I just mentioned, it expresses in the soluble form. If we look at the structural criteria, if we do via circular dichirism and look at the secondary structural content of this highly alpha helical protein, that secondary structural content of this water-soluble form now is consistent with what we see in the membrane-soluble form, that it's tetrameric in solution, just that the wild type is a tetramer. And we can also look at binding. So it turns out that this toxin, the scorpion toxin, binds specifically, so you can do competition studies with other generic proteins floating around. It has an association constant that's comparable to what's observed in the membrane-soluble form. It binds with the same stoichiometry, the 1 to, I guess you could say 4 to 1 stoichiometry. And you can compete it off with small molecule ion channel blockers like tetraethylammonium. All right, so in that respect, this water-soluble variant at least behaved a lot like the membrane-soluble form. And then in 2008, a structure came out that was determined via NMR methods. All right, so here's 2 of the 4 different subunits superimposed with the crystallographic structure. So the crystal structure is shown in the gray or white, and the water-soluble form that's determined via NMR is shown in the sort of amber or the orange and green. And the orange residues are those that were mutated so as to confer the water solubility to the protein. And we can see that more or less in terms of both the tertiary and quaternary structures of these 2 proteins, they superimpose pretty well. There is some slight variation in the selectivity filter, which is the important part for the potassium ion selectivity. But this is highly, and we can see from the ensemble of structures that it's a relatively well-defined structure as well. So this is really encouraging. We've since gone on to apply this to other types of proteins. One in particular is the human mu-opioid receptor. So this is a different class of proteins, but again, integral membrane proteins. This is G-protein coupled receptors, or GPCRs, an important class with regard to a lot of medical chemistry. All right, so the human mu-opioid receptor is involved in some cells that further signal basically neurons that are associated with the inhibition of pain. Right? Usually this is associated with so both the brain and spinal column. That small molecules bind to this integral membrane protein and elicit further signaling. And here's examples. So a wide variety of usually heavily controlled substances are the molecules that bind to the human mu-opioid receptor, like morphine, naltrexone, fentanyl, and a number of others. So here we have one agonist, one that elicits a response, the pain response, and an antagonist that basically elicits no response or prevents binding of morphine. Okay, So this is a collaboration at Penn, and also collaboration with a group of Renyu Liu, a physician at Penn, in the group of anesthesiology and critical care. So most of the experimental studies were carried out in his group. Jose Manuel Perez Aguilar, again, is another native of Mexico. So he's from Puebla, went to the university there, and then did his graduate studies at Penn, got his PhD there. He did a postdoctoral fellowship in New York at the Cornell University Medical Center. And now he works at IBM, the company, in their computational chemistry and computational biology division. So when Jose started this project, or say Jose Manuel started this project, that basically we had no structure of the human mu opioid receptor, so we had to build one. And so we looked at related structures of G protein coupled receptors, and we aligned those sequences, and then we built a guess as to what the structure would be. So this is well known. This is referred to as homology modeling or comparative modeling. Since that came out, all right, our structure was determined. Let me see if yeah. Since we built our model structure, the Kobilka group at Stanford determined a structure of the mouse form. Let's see, do I have that? The mouse or the murine structure. And we can see that they more or less superimpose, particularly with regard to these transmembrane spanning regions. As with most G protein coupled receptors and many integral membrane proteins, they differ quite a bit with regard to loops in these extracellular regions, but we're not really focused on making changes in those positions. It's more these lipid contacting residues. So that was used to then identify residues to vary, residues to target for mutation, exposed hydrophobic amino acids, right? And that's what's colored in purple or magenta here. And so then we apply the calculations, allowing each one of those to vary in the context of the model structure, and we identify now what should be a variant that we think may be water-soluble, and indeed we can express this in E. coli, we can purify it, and then we can show that it's largely monomeric in solution. And now we can do competitive assays with cellularly expressed human mu opioid receptor, and their competition for a labeled ligand, naltrexone, an antagonist of the wild-type human mu opioid receptor. And what we can show from that study is that we get an affinity that's, again, comparable to the wild-type membrane-soluble form, which I think is on the order of 50 nanomolar. Right? So this does involve variation of large amounts of the protein, 55 residues out of roughly 288 different positions. Right? And we got a variant that. For this, as yet, however, we have no high-resolution structure either using NMR or crystallography. And so we're looking to see if there's other tracks we can go to get more structural information. But it sort of suggests now we have a construct that we can generate and make in large quantity. Is there other things we can do with it? And one thing we've done in collaboration with a group in the Department of Physics at the University of Pennsylvania, so Charlie Johnson's group, right? So what his group is able to do, and I'll go over this briefly, but his group is able to make high-quality graphene and two-dimensional materials and make these in a nanostructured sort of array or configurations, so you can make sort of ribbons of graphene. Then the order of sort of microns or less in dimension. And that once you have those, you can build what are referred to as field effect transistors or electronic devices that are able to basically, you apply gate voltage and you can monitor the source drain current just like you could in many transistors. And so his group has looked at functionalizing these types of electronic devices with a wide variety of biomolecules. This includes DNA, this includes a wide variety of different types of antibodies, other types of proteins. And because these types of systems, the graphene and the other two-dimensional types of materials, their electronic structure is highly sensitive to the local environment, that if there are changes with regard to the display, for example, of ionizable groups, of charge, of what residues contact the surface of the graphene, oftentimes those can be read out now directly in terms of an electronic response. Right? This precise molecular details is oftentimes hard to piece out, and that's still an ongoing area of research. So what we did in this case is that we could functionalize now these graphene surfaces with this water-soluble variant, the human mu opioid receptor. We could get it in large quantity. There are a variety of ways to do this. You can chemically modify the graphene surface and introduce defects that are reactive, and then oftentimes a primary amine or a thiol will react with those defects on the surface. A much gentler and a much better way that they found is to simply attach a large hydrophobic planar group to your molecule, your protein of interest, like a pyrene or a condensed aromatic, and oftentimes then you'll have a high affinity non-covalent association of the protein with the underlying graphene surface. Right? Then we can look at just exposure to the ligand, in this case naltrexone, an antagonist to the human mu opioid receptor. If we look at the source drain current as a function of the gate voltage, this is something that's commonly observed, I'm told, for these two-dimensional materials, particularly for graphene, that we see this sort of non-monotonic behavior. This point of sort of minimum current is referred to as the direct voltage. Right? And this has to do with basically the large-scale electronic structure of the underlying graphene surface. And what's seen is that you can now look at, for these protein functionalized devices, you can look at now their exposure to the corresponding naltrexone. Naltrexone will bind, there'll be some sort of change in the structure of the protein, usually a slight readjustment of the helical content, elements with respect to each other. And that can be picked up or read out as a shift in this gate voltage. Exactly how that applies is something that the Johnson group is still trying to work out. But we can look at the magnitude of this shift as a function of simply just the concentration at which we expose naltrexone to this particular type of device. And then we can fit that using standard sort of chemical equilibria techniques, sort of Hill isotherms or Hill-Langmuir isotherms. And we can get a fit, and we can get an estimated affinity that's, again, within the same sort of regime that we see for the wild-type receptor. And then we can see we can go down to very low concentrations of the naltrexone that's present and still achieve a recognition or a signal that's well above the baseline of these types of devices. Okay, so I think that's where I'll stop. I just want to thank everybody that was involved, particularly people associated with my group and some fantastic groups to collaborate with, and the funding agencies. And I'd like to thank everybody here as well. And I'd be happy to try to address any questions.
Thank you very much. Si tuvieran alguna pregunta, comentarios. Bueno, pues si no, vamos a detenernos. Agradezcamos nuevamente al profesor Seven. Pues vamos a tener entonces un receso, aproximadamente media hora, un poquito más, y pues es claro una oportunidad para platicar con nuestros invitados, los conferencistas el día de hoy, y espero que pues todos aprovechemos esta oportunidad. Muchas gracias. Thank you so much.
Su atención, por favor. Su atención, por favor. Invitamos a que nos acompañe a ocupar su lugar en el auditorio, ya que en breves instantes continuaremos con las exposiciones de esta mañana. Su atención, por favor. Su atención, por favor. Invitamos para que pase al aula mayor, ya que en unos instantes continuaremos con los trabajos de esta mañana. Por su atención, gracias.
Si les parece bien, vamos a continuar. And I have the pleasure of introducing now Professor Daniel José Mindiola, who was born in San Cristóbal, Venezuela. I won't say the year, but he's very young, yes. San Cristóbal is a city located in the southwest of Venezuela, in about 45 minutes from Colombia. Professor Mindiola moved to the US with his mother in 1989 and obtained a Bachelor in Science degree in chemistry from Michigan State University. Daniel then attended the Massachusetts Institute of Technology, the famous MIT in Cambridge, under the guidance of Professor Christopher Cummins. Daniel explored several areas such as arene extrusion reactions and the synthesis and reactivity of low-coordinate metal complexes. After 2 years at Chicago, Daniel accepted an invitation to join the chemistry faculty at Indiana University in the city of Bloomington. In the summer of 2013, and after 11 years in Bloomington, Daniel moved to the University of Pennsylvania, where he presently holds a presidential chair professorship. In 2014, Daniel was elected as Fellow of the Royal Society of Chemistry and is presently Associate Editor for the ACS journal Organometallics. Today, he will deliver the talk, Doing Better Things Than Just Burning Hydrocarbons, Catalytic Dehydrogenation of Volatile Alkanes with Titanium. Please, Daniel.
Thanks, Eusebio, muchas gracias. Esta es la segunda vez que vengo a visitar la ciudad de México y siempre ha sido un gran placer escaparse del clima que estamos sufriendo ahorita en la ciudad de Filadelfia, ¿no? El clima frío que estamos pasando por ahorita en el invierno. Pero sí, es un placer estar aquí. No voy a dar mi discurso en español, voy a darle más trabajo al traductor aquí de la química que voy a presentar, porque si no se me hace duro mucho tiempo pensando en las palabras que voy a usar para este discurso. Ok, como Eusebio te mencionaba, we're working with, the title sounds a lot better in Spanish, reads a lot better in Spanish, so I had to put it in Spanish here. We're trying to find better ways to convert hydrocarbons that are often thought as just fuel sources for the sole purpose of warming our homes, and using those as precursors to generate much more value-added products like alpha olefins. Especially for alpha olefins, it becomes a lot more challenging. And we're using, of course, hydrogen acceptors, so we're cheating around the thermodynamics of this reaction, and our byproduct is, of course, also a useful molecule such as methane. So some of this work started at Indiana University and has evolved quite a bit at the University of Pennsylvania. So I must put a sign of caution here. Please read it. So the translator has to read it now in English to our speakers, but basically it is a warning sign telling you that what you're going to see from now on is going to be high dosage of organometallic chemistry. So I'm just giving you that caution. So viewer discretion is advised. So here is a summary of what we do in my lab. I'm not going to spend too much time discussing every project that my group does. Rather, I'm going to tell you a nice, beautiful story that evolved from a very fundamental study all the way to what we think it's a very unique area into catalysis that involves dehydrogenation of linear alkanes to alpha olefins. So we're pretty much all over the periodic table. I didn't show uranium, so we actually work with uranium 238 as well. That's an ongoing project with Professor Carsten Meyer in Germany. But we like to study metals that, in particular these from the 3D series, that tend to be electronically confused. I refer to it electronically confused in the sense that they have unusual electronic structure. So we like to work with radicals, metal radicals, in as much as looking at transformation involving these metal radicals. So a lot of the effort is spent with early metals, so we do look at early metals, and we're interested in a lot of mechanisms, CH activation. We're now getting into cyclic polymers. That's an ongoing collaboration with Adam Beej. Mookie Baik at KAIST in South Korea has looked into a lot of the reaction profiles using high-density functional theory. And we also move our way to the right. So again, these are metals that now have much more redox versatility. So we can look at perhaps two-electron chemistry because you have access to multiple oxidation states, and there we're striving to do catalysis with these metals. And as well, we're looking into electronic structure, magnetism, as well as unusual coordination environments with these metals that become a little bit more difficult to characterize because they have unusual electronic states. And in the past, we've looked at the coinage metals, more recently at iridium, although I try to stay away from precious elements, but it turns out that these are really a tour de force in the area of CH activation and catalysis. And much more recently, a collaboration. If you've looked at the slides from previous speakers as well as future speakers, you'll see that Penn is quite unique in the sense that we have a lot of intra-departmental collaborative efforts. Science is becoming, especially chemistry, is becoming a multidisciplinary area. And so we must combine efforts to understand some of these much more complex systems. So NMR techniques, it's just really a good sense of a lot of different spectroscopic techniques, including very specialized ones like high field, high frequency EPR, and that's the work by Josh Telser. Okay, so today I won't talk about all the elements that I just put in the previous slide. I'm going to talk only about one that lies in my heart. That's titanium. That's a group 4 metal, and it does have somewhat redox versatility. You can access the +2 all the way to the +4 in well-defined systems. So you can technically do 2-electron chemistry, which is instrumental in the building of CC bonds if you want to do coupling or catalysis with it. So these are my dream reactions. There's several problems with this. So if I show this to a freshman chemist, immediately they should recognize that this is an uphill battle and I'm doomed. I'm never going to get funding for any of these reactions because you're going uphill. You're breaking stronger bonds to make weaker bonds. Right? So just based on the thermodynamics overall and the bond strengths, these reactions should not be favorable if we exclude entropy. So this is one where you have a linear hydrocarbon. These are certainly natural resources that we essentially just use as a source of olefins nowadays, but also as a source of fuel. And you're basically doing a dehydrogenation. You're removing hydrogen, oxidizing the product, and I'm just showing hydrogen as a side product, but concertedly you could show it as H dots that could also be formed in this type of reaction. And ideally we want to find a catalyst that can perform this reaction, which is thermodynamically uphill. Right? So you're saying, well, that's going to be difficult. The way you can get around thermodynamics now is by quenching the hydrogen, finding a hydrogen acceptor that can then get the reaction nearly isothermal at higher temperatures. And so that's key. You can get around the thermodynamics by finding ways to use the hydrogen and break that HH bond and perhaps make CH bonds in the process. So you're doing dehydrogenation to actually do hydrogenation. So in a way, it's overall isothermal. You can also look at more challenging reactions, and these are catalysts that ideally you want to dehydrocouple methane and make now a building block like ethylene that's for essentially a building block for a lot of different materials, including polymers and epoxides, which are essentially building blocks for a lot of pharmaceuticals. And these, again, are uphill, a lot more difficult than in the case of the dehydrogenation shown above. So you can play around with the thermodynamics and make these reactions a little bit more towards isothermal. Like I said, you can play around with hydrogen scavengers. You can also do tandem catalysis to make the reaction fall a little bit more into the negative delta G. And of course, negative delta H. And certainly you can overcome delta H with the T delta S by increasing the temperature, right? So that's certainly a very obvious strategy here. So there are ways to kinetically control this reaction. So this poses as another challenge. Because you're doing a dehydrogenation that's selective only for the terminal position. Right? You can easily say, well, why can't we activate at the internal position? And it turns out that reaction would be more thermodynamically favorable if we go in that direction, because internal olefins are thermodynamically more stable than their alpha olefins. And counter to that is the fact, the paradox of that is that alpha olefins are more useful than internal olefins for a lot of wide array of reactions. So there's ways to get around that, and I'll show you that in a minute. So how do we get olefins? I mean, these are not naturally abundant. They are present in crude oil, but in small fractions. So the way you get around this is you use a very simple, very cheap at the time process, and that is referred to as steam cracking. So steam cracking is where you collect the ethane from natural gas or from shale gas, which has a higher content of ethane, roughly even up to 15-16% content. You bake this up to about 800 degrees with high velocity steam to avoid over-oxidation. So these are essentially plants that you have steam columns there to run the gas at very high velocities with the steam. This is Okay, you can get as cheap as that. You can't beat water, right? But the problem with this system is that you form a lot of CO2 via the process of combustion because you have to generate this energy from somewhere. Typically, it's coal. Now they're using methane as a source of fuel, so it's a little cleaner, but still it's not practical from a renewable point of view. And the other source of carbon dioxide is in actually looking at this reaction. So what you're doing is breaking the weakest bond, which is the CC bond. You make radicals. Those radicals then undergo through a hydrogen atom abstraction and generate other radicals, which can couple, undergo further abstraction processes, and that's how you make ethylene in the process, as well as alpha olefins, which I'm not showing here for clarity. So this is the main source of alpha olefin in the United States and in North America. So let me clarify to my colleagues, esteemed colleagues, that North America is not just the United States. It actually encompasses Mexico as well as Canada. And so those are basically using this as the main source of ethene. And just to give you a rough idea, this is 4.1 billion liters per month that are being produced through this radical chain reaction process. The other source of CO2, as I alluded to, was the fact that you make methane as a side product. When you have methane in water at those temperatures, you begin to see steam reforming taking place, and that results in hydrogen, which is actually a detrimental process for the steam reforming because you start doing radical chemistry and hydrogenating your olefins. So that's one of the limitations of the system. Well, you can burn as much coal, and now with the Trump era, certainly this is going to become better, right? We want to burn more coal and generate more pollutants in the environment, but that has to come from a source, right? Where's the energy coming from? And so we're trying to find better ways to generate olefins from a more practical standpoint, as well as more selective, rather than radicals. So ethane just doesn't come from, a very small fraction of ethane is present in natural gas, but let me just clarify, shale gas is becoming a hot commodity because it has higher content of ethane. And so ethane is being the major supplier of alpha olefins now in North America. So one of the reasons, I don't tell this to my chairman, is that we're sitting in a pile of a nuclear bomb, essentially, here of shale gas and natural gas, and that's one of the reasons why I moved from the Midwest to this red, a little bit closer to the red Marcellus reservoir that contains a high amount of methane and ethane and some propane in there. But there's also certainly a lot of it in the Gulf of Mexico, and if we really want to run out of natural resource, we should power the planet for the next 50 years and generate all that energy, right? But that's not really what we want to do here. We don't want to run out of stones to think of the next Neolithic era. So what are the uses of methane? Well, the first one is you can do combustion. Certainly that's quite useful. It's a very good reagent for combustion when pure. It releases energy quite effectively, grams per mole. But again, a gas doesn't generate a lot of weight when you think about it, so it's certainly very clean when it's pure. But the major industrial use of methane is through this process called steam reforming, which is coupled, in some cases unavoidably, with the gas shift reaction, water gas shift reaction. This is a little bit easier to do. You need catalysts for this reaction to go. This is much more energy intensive, but this is how we get hydrogen out of methane through this steam reforming process. Why do we need the hydrogen? It's not to power our vehicles. That's actually not the main use. The hydrogen is being used to generate ammonia, which is essentially how we're feeding our planet nowadays through the Haber-Bosch process. So this is really the combination of these two steps, this one and that one, is what's leading to about 3% of the energy consumption in the world is because of this source of hydrogen and usage of hydrogen. So when we think of a hydrogen economy, think again where that hydrogen is actually coming from, right? It's not coming from water, at least not in a practical sense. It's coming from a non-renewable, still today, non-renewable source like methane. So it's really, methane is keeping us alive now. And as you know, most of your nitrogen in your body, about 70 to 60%, derives from this anthropogenic source of ammonia. So there's too much of methane, and this is the alarming part of it. The reasons why there's too much of it is certainly a naturally abundant, but there's not enough storage capacity for methane. So what do? They burn it, and the reason they burn it is because it's a powerful greenhouse gas. It's approximately 25 times worse than CO2. And so they burn it, and they release 2 greenhouse gases in the process, and it's estimated in the U.S. alone that this is it depends on the source of natural gas. So prices vary according to regions. So it's hard to estimate what the cost and loss is, but it's estimated that it's between $50 to $100 million annually that's being burned away. And more recently, especially coupled with these alarming numbers in the state of California, another 50 to 100 millions are actually being lost through leakage. Right? So this is quite alarming for environmental reasons. Yeah. So this is a satellite map of the United States, part of Mexico here. But you can see that the highly dense, highly populated areas are lit up like a Christmas tree. And then you have these non-residential, highly populated, non-highly populated components that are lighting up also as a Christmas tree. And it turns out that these are the flare stacks that are burning day in and day out in the North Dakota state, right? So there's not a lot of folks around there, certainly not comparable to Chicago or the northern eastern seaboard. So this is why I like funding in the U.S. nowadays, because I'm in a special position where we're looking at natural gas on the rise, right? So this is going to fund a lot of the work on natural gas. We see coal on the decay, right? So this is projection by the Department of Energy. You're decreasing. Petroleum is also on decreasing. You have biomasses right now presumably hitting a brick wall, but it is still showing growth. And of course, you have other non-renewables that are also showing some growth. This is, of course, a projection before election took place. Now this is the projection, right? We have deportations. A lot of energy is going into deportations, women's fashion, anti-environmental groups, hate groups, right? So my funding is going to decrease significantly for the next 4, hopefully not 8 years ahead. And natural gas is going to be on the decrease, and coal is going to be on the rise, right? Now, I show the wall of Mexico that separates Mexico and the U.S. as only 5%, because this gentleman is expecting the other 95% of energy to be coming from Mexico for the building of the wall. Good luck. So let's go to chemistry now. We have we're inspired by a lot of this chemistry that was published back in the 2000s. This is work by Couperay and Basset, as well as by Chevron Phillips, even as early as 1973. They were interested in finding ways to recycle tires. And this area is called alkane metastasis, but really the nomenclature is incorrect because you're not really breaking CC bonds and making new CC bonds, at least not concertedly. So one reaction that caught our attention is we can grab natural gas, or they could grab natural gas at around 500 degrees. Remember, this is an endergonic process. You can do it on a surface. These are proposed intermediates. I'm not going to discuss all these intermediates. And you can dehydrocouple that to make ethane. And this is a big deal reaction. You're making a hydrocarbon that's pretty much used for burning, just like another hydrocarbon that's used for burning. But this one, as you know, is very useful in the steam cracking process to make alpha olefins, right? So this is a building block, unlike methane. And you also make ethylene in the process, a small fraction of this. So you're actually doing dehydrocoupling again to give you ethylene, which is even more useful, directly out of methane. What caught our attention is not so much about all these silicate-supported surfaces. These are, of course, transient intermediates that are formed. We're interested in the role of the metal-carbon multiple bond in these sets of transformations. They're integral parts of this. They play critical roles in not only the CH activation step, but also in the CC making step, right? So could we devise a system that's well-defined, characterize it, and then do these similar transformations, ideally under much milder conditions? Of course, we're tricking thermodynamics. We need to use a hydrogen trap to drive the equilibrium, at least, towards products. There are systems that are homogeneous, and this is the work by Alan Goldman, really beautiful work at Rutgers. He's developed systems inspired by Crabtree and others, basically in the area of alkane transfer dehydrogenation. So what they're doing is they're transferring from the alkane those hydrogens to make these reactions nearly isothermal at diffusion control temperatures. Right? These are milder, of course, but you need to do the hydrogenation for this reaction to go. Now they've developed strategies to get around this by purging the system or doing tandem catalysis. The reaction does generate alpha olefins in the process, but the problem is that with hydrides present, you can start isomerizing these catalytically to the internal olefins, and that kills a lot of the chemistry because, as I mentioned before, these are thermodynamic, the internal olefins, with respect to the kinetic products. So we don't want to get into a situation where we're doing dehydrogenation then to make internal olefins that are much more difficult to use as value-added materials. And this is a proposed reaction. I have to mention this mechanism because our mechanistic step has to be different from what's been proposed by Alan Goldman and Brocard and others. So they propose that this undergoes a reductive elimination step to make an iridium, unsaturated iridium-1 species, which then activates, and they're using cyclooctane as their substrate, cyclooctane here, does oxidative addition to give you the product shown here, iridium-3, and then the key step is beta hydroelimination releases the olefin and makes a hydride, and then you're back to the resting state of your catalyst, right? If you're making hydrides, then obviously you're going to get into a situation where the terminal olefin gets isomerized. Why does it go for the terminal? Well, there's a kinetic control that does that. So it's both kinetic, a little bit of thermodynamic, but mostly kinetic based. So hydrides are no good for this reaction if we want to have selectivity towards terminal olefins, and we want to also reduce those temperatures as well as get into milder conditions. Right? And these, of course, are non-volatile type of hydrocarbons. So this is where my research gets into play. We're looking at early metals. We're also looking at later ones. But for catalysis right now, we're looking at early metals as well as heavier metals like iridium and osmium. But titanium is a base metal. It has redox versatility, as I mentioned. It is really air sensitive for a lot of the systems that we have. But we want to engage in the role of metal-carbon multiple bonds. And they're highly polarized, so they're really super basic. And perhaps they could do CH activation that way. But as you know, titanium carbon bonds are building blocks for polymers, right? This is well-known. Ziegler-Natta catalysts are still, some of the best are still titanium and zirconium based. So can we use these metal-carbon multiple bonds to do these types of transformations? Making olefins out of hydrocarbons, linear alkanes, is difficult for many reasons. You don't have a lot of very high ionization energies, binding affinities, so it's very difficult to do that under mild conditions. So here's where our chemistry takes place. We're looking at a pincer ligand. I'm going to draw it as a cartoon shown here for clarity. And basically, this is our building block. And Brad Bailey, almost a decade ago now, more than a decade ago, that sounds scary, generated this complex and found that you could activate benzene at room temperature. It takes about 12 hours for this reaction to be complete at room temperature. And I won't bore you with all the kinetics. This is about 5 years of kinetic data, not only from Brad's work, but also Alison Fout. We found out that this is not a concerted reaction. This is, in fact, we propose that it's going through an alkylidine, very high energy species. So this group deprotonates at the alpha position. You make a nearly square planar titanium-4. That's what generates a highly reactive polarized metal ligand multiple bond. We chose this ligand for a specific reason, and that is it's constraining titanium to an unusual coordination environment. That leads to a very high energy molecule that activates by 1,2 addition the CH bond of benzene. So this is not the hard step. Activating the hydrocarbon is not hard. It's making the molecule that activates the hydrocarbon the rate determining step. So we can also activate methane. Right, so methane, we need the high pressure. When I say high pressure, it's 300 psi or so, or higher. These reactions have to occur in the absence of water and oxidants for obvious reasons. And we've done a lot of isotopic labeling, kinetic isotope effects, and pretty much the mechanism suggests that this is also proceeding by the alkylidine that I showed here. Right? So it's very reactive. It activates methane like it's going out of style. How do you translate that in Spanish? Where's our translator? Like it's going out of style? There you go. Okay, the rates are indicative that we have the mechanism that we propose here. I won't bore you with the data here, but you do have an isotope effect, a primary isotope effect that's doing that. Pressure doesn't change the rates. Don't be deceived by this reduction of the slight rate, because in the absence of methane, we see rates that are within the same order of magnitude. So again, making the alkylamide is rate determining, not activating it, not activating methane. So what can we do with this? So we were looking into ways to dehydrogenate methane. And so Jaime Flores, he's actually not from Mexico, he's originally from Peru, did the work that I showed you here. He did a lot of beautiful isotopic labeling studies. And what he found out is that we can dehydrogenate methane, which I'm still really excited about this because now we have a way perhaps to do carbene coupling and make ethylene. So with these radicals, technically they could behave as radicals. So we can activate methane at room temperature. It takes about 12 hours. These are all first-order reactions, pseudo-first-order reactions, rates in the order of 10 to the minus 5 per second. So when he labels this position with deuterium, he sees very cleanly that it goes away. It washes into the methyl group, and you begin to see this grow in the proton NMR. So we must be proceeding by unmethylidine via a tautomerization. However, the rates for elimination of methane under these conditions, because it's very slow, these rates are in the order of 10 to the minus 6, so much slower. Unfortunately, we can't discard this other pathway where you have elimination and then, again, addition. So you can see that you have very little label of deuterium, and then it kind of grows into the proteo. And then it goes away because you start losing the methane. So what can you do? We can do ethane as well. In the case of ethane, now you put a Mexican to the challenge, and he'll do it. So Marco Crestani, actually a former PhD from the group of Juventino Garcia UNAM, did some really beautiful work characterizing these molecules that are challenging because you have a lot of diastereotopic hydrogens, and so it becomes much more challenging to characterize this. What Marco found out is that with ethane, you go through the alkylidine, the kinetics show that, and you make an olefin now. So now we're doing dehydrogenation at room temperature of a substrate that typically you don't think is a reagent. This has to be done in high pressures. You can liquefy ethane above 750 psi, so it's actually, for storage capacity, ethane is actually much more useful than methane. But this reaction does an intramolecular dehydrogenation, and notice where the hydrogens are going. They're ending up at this position here. So you can actually heat these up or oxidize it to release the olefin, the ethylene. Quantitative, these are reactions that are quantitative, but the problem is that you don't have a way to recycle these to do the reaction catalytic, right? In the case of linear alkanes, we see the same thing. We see activation. You expose this to pentane and pentane. These are linear alkanes. There is no isotope effect. So again, activation of the hydrocarbon is not the hard part. And when you see a mixture of isomers, we thought initially, gee, this is activating both terminal and internal. We have no selectivity here. But it turns out that the selectivity is there. When you oxidize these, you make only the alpha olefin, and that's exciting. So what are these isomers? Turns out that these isomers, you have formation of the alkylidine, activation, selective at the terminal position, so this is kinetically controlled. Then you have an abstraction step. That gives rise to the two isomers. What are those isomers? Well, remember, these ligands are not planar. They actually have chiral, axial chirality, and you have a chiral carbon there, so you can technically have as many as 16 isomers due to the orientation of the olefin, the axial chirality of the ligand, and the position of the R group, as well as the position of the T-butyl in or out. So we are lucky to see two isomers, which we believe are the two diastereomers that in solution that technically we might have 4 enantiomers there. But regardless, it's all selective, so we make the terminal olefin. And you can go down the series. So let me just summarize here. You can do propane to propene. This is a big deal reaction if we could do it catalytic. This is all stoichiometric. So now you wait 12 hours, you add a quenching oxidant, and you make only alpha olefins. For these alkanes, all these alkanes are not very useful as liquid fuels. They have high volatility. They can't be used in a regular engine, a piston-based engine, because they result in a lot of knocking phenomena due to incomplete combustion in the chamber. So you want to convert these to more useful products. And so this is where Masa Kamitani looked into a way to do a catalytic reaction. Can we look at a reaction now where we have a linear alkane, a carbene source, and then we make the alpha olefin, and we're doing essentially a transfer dehydrogenation. That's what we're doing. But instead of using an olefin, we're using a carbene as our trap. Now, carbenes, you can't just buy triplet carbenes from Aldrich. You have to generate these things, so it becomes challenging. So what we're doing is selective activation, selective beta activation, then an oxidation to regenerate the precursor to the alkylidine. It turns out that diazoalkanes don't work as a source of carbenes. They're too reactive. They react pretty much with all these intermediates. Ylids become the next obvious choice. And it turns out that we looked into this common ylid, this triphenylphosphine methylene ylid, and it doesn't work. It gives us interesting chemistry, but we're seeing PC activation in the process. Remember, you're going through what I would refer to as a titanium 2 formally, and so those can undergo oxidative addition, and we see oxidative addition of the PC bond. So this was really a clever way that Takashi Kurogi, a postdoc in my group, as well as a former grad student, Doug Soloway, basically came up with their own idea. They said, how do we get rid of this phenyl migration? Well, let's tie 2 up, right? Let's chelate it to make a biphenyl, and that statistically should reduce the probability of the phenyl to migrate by 2 orders of magnitude, at least. And that is assuming that that step might be slow. So they made the ylid, and they found out that sure enough, it doesn't behave structurally very different from the triphenylphosphine. So these are 2 superimposed structures. When you expose this molecule at room temperature with cyclohexane as our testing solvent, you see cleanly, quantitatively, room temperature after 12 hours, cyclohexene, the phosphine has done its job. The other beauty of this phosphine is that it precipitates out, so it does not poison the system. We're very lucky with that. You make the hydrocarbon, and you've transferred the methylidine from here that also behaves like a hydrogen acceptor. All right? So our mechanistic scenario allows us now to do catalytic transfer dehydrogenation with a base metal, and we can test the selectivity of this. So this is the reaction I just showed you. You make the alkylidine. This is the rate-determining step of the reaction for this precursor. Cyclohexane comes in, it gets activated, right? Here it doesn't matter because these are all equivalent, but in linear alkanes, you have a kinetic preference for the terminal position. Then you do the selective beta hydrogen abstraction. This accepts another hydrogen from the alkyl. This is an intramolecular process. It looks like I ran out of battery here. This is an intramolecular process, and you don't go through hydrides. You do not go through hydrides, and that's key, right? Because then you don't isomerize. Then a dissociative mechanism. This poses as other challenges because you go from a singlet to a triplet surface. So you're doing spin transitions here, spin for bin transitions that we do not want to get into with 3D metals. And then this does its job, delivers the carbene. We know from methane that we can go through these species. Then this tautomerizes, eliminates, and you're back to your promiscuous reactive molecule. Right? So what can we do with this? And I'm sorry, the battery died on this. I don't think this. Oh, there we go. So it took us about 13 years to get all these rates. Is that pathetic? Right? So 13 years of PhD studies and postdoctoral studies. Initially, this is very scholar, but what useful information can kinetics give you? So if you look at the rates, I'm not going to bore you through all the detailed spectroscopic and mechanistic work, but the rates are key. These are rates that are comparable, and then you get to this last step, and all of a sudden, that rate slows down significantly. This is our bottleneck for that reaction. But here's the beauty of this. We can optimize that rate, and we can get it as low as 10 to the minus 4 per second. So changes in the delta G of 1 kcal are huge per mole, right? So order 1,000 times in the rate. So it can make differences. And we're looking into that. We could do the reaction at room temperature. So here's the important aspect. Yeah, thanks. Here's the important aspect that we can now do catalytic reactions. Now, this is 75 degrees because of that bottleneck. We get a whopping 3 turnovers of this reaction. But it's the first example where you have a base metal doing this type of catalysis by a different mechanism, completely different mechanism. And this is our catalyst. We don't have to start from this catalyst, but we do want to start from it because this elimination occurs at room temperature. This one does not eliminate until you get to 75 degrees, at least in a few hours. Next. Oh, thank you. So here's our table of reagents. Notice the reagents we're looking at, right? These are the least inert of substrates that you can think of. They don't have any type of functional group except CH bonds. So we can do cyclohexane to cyclohexene, cyclooctane to cyclooctene. Okay, these are not the best turnovers. It's not selective because you don't have discrimination between CH bonds there. But when you get to linear alkanes, you get exclusively only alpha olefins. We think that this is much higher, except that we lose our pentene to the gas phase, so our yield, our error bars tend to be a little bit high. But you can see very selective for alpha olefins. We're optimizing this reaction, but it should be catalytic as well. This is very important because one butene from butane, now you have, instead of using it for a lighter fluid, you're using it for an alpha olefin, which would be a big deal. Now, granted, the ylids as hydrogen acceptors are just not economically viable. So this is our catalyst. These reactions take a few days, and they occur at 75 degrees. This is a reaction profile. It looks like a nightmare, but I want you to just focus on one step, and that is the elimination of methane from this to regenerate our active state of the catalyst, which is the alkylidine. That barrier is around 32 kcals per mole. That's why we need 75 degrees. That's also affecting the elimination of olefin because you go through a spin transition, spin for bin transition, and thermally, those are a mess. If you want to heat those up, it actually worsens the reaction. But now we have a way to improve this, and this is where the rates are important. We can optimize this reaction because all we have to do is put a better delivery carbene vehicle, a larger carbene, and that barrier goes down by as much as 5 kcals per mole. 5 kcal. This is the delta G. That's going to make, we're going to get thousands of turnovers. Granted, we're going to deplete the world of ylid, right? We know the mechanism. We know that this elimination of methane to make the alkylidine and 1,2 activation, this is not the important step. It's this one. This is the rate determining step. Experimentally, a little bit off from the theory, but it's around 28. Right? And we see a kinetic isotope effect if you label those positions. So I just want to emphasize that there is hope in the early transition metal series, and the key here is that the beta abstraction, unlike beta elimination, is leading to no hydrides, and that is where the selectivity that we observe. And then the final slide, before I acknowledge those who did all the chemistry here, is we have these superb labs. We're desperately looking for personnel. So please raise your hand, and I'll ship you back to the U.S. Or ship you to the U.S. Please. We need hard workers, thinkers in the lab, and I'm showing you half of the lab here. We have 2 other glove boxes in the back as well as hoods. Our nitrogen, this is the forming gas for regeneration, but our nitrogen is coming from the atmosphere. So I think we're the only lab in the world that has capabilities to extract, because we work under anaerobic conditions, we extract nitrogen and purify it to 10⁻⁶ ppm of oxygen to deliver that with non-cryogenics into our boxes. We can generate as much as 4,000 liters per minute of really pure nitrogen. And the other aspect that Professor Gary Molander mentioned in his talk too is that the high throughput facility has been instrumental at Penn, and it allows chemists not only to make molecules but also probe these for applications and screen them. So this is a 96 well high pressure plate essentially that we could test and screen catalysts under high pressure of hydrocarbons. So not only do you have to work under homogeneous systems, you can actually do multi-phasic conditions as well. And you can read that in a recent paper. So these are collaborators that we've had in the past and in the present. Let me see if I see him. Miguel Munoz, he actually got me here to here in Mexico the first time, and he's in Cuernavaca. And Francisco Zuno is also a wonderful friend that invited me to some of the chemistry at Pachuca that I didn't have time to show you there. So these are this is an outdated picture, but basically we have a lot of, this is all funded by the National Science Foundation, and it was for some time funded by Chevron Phillips until I moved to Penn. So with that, I thank you for your attention. Gracias.
Muchas gracias. Si hubiera preguntas o comentarios.
Pueden también preguntar en español.
Por favor.
Bueno, aprovechando esa invitación a preguntar en español, lo que se ve en los gráficos de PAI es que va a haber muy poca evolución en el consumo de petróleo y va a ganar muy poco, de 2011 a 2040 va a ganar muy poco el consumo del gas natural. Finalmente, ambos productos van a ser usados como combustibles. Es realmente de lo más penoso saber que los hidrocarburos se utilizan más como combustibles como otras formas de beneficios pues, para la humanidad, ¿no? Pero esta evolución…
Muy lenta evolución, por
muy
cierto.
lenta, muy lenta, y vamos a depender mucho tiempo de esto. Bueno, está muy atenida o tiene mucha esperanza en que se siga produciendo el shale gas y el shale oil. En el caso de la parte central de México, pues las lutitas son más productoras de petróleo que de gas, mientras que hacia el norte es donde más de gas que de petróleo por la constitución de la materia orgánica, ¿no? Pero el asunto es que finalmente vamos a tener ese pronóstico en cuanto al consumo de energía. Realmente el paso que deberíamos de dar es hacia a la transformación de los hidrocarburos en otros productos útiles y avanzar más en energías pues más limpias, ¿no?
Sí, claro.
Pero yo veo que esto de la de hidrogenación está muy basado también en la utilización de energía y también en el aprovechamiento del gas de lutitas, quizá también del petróleo de lutitas. En el caso, esto no se opone, o sea, no vamos a terminar usando más energía en producir de hidrogenación para después producir otros productos de hidrocarburos.
Sí, bueno, muy buena pregunta. Yo creo que el problema es, tienes razón, de que estamos evolucionando lentamente del carbono al gas natural como fuente de energía. La única ventaja que se ve en eso es que hoy en día si el gas natural está purificado, crea menos contaminante al ser quemado prácticamente como fuente de energía, me estoy refiriendo al carbón, ¿no? Al coal. Ese es el único beneficio que se le ve en esto. Y ahora tiene el sistema donde tienen paralelos, en reacciones paralelas en la industria, donde tienen el gas natural y el mismo gas natural que se está usando para el steam reforming se usa para combustible para estas crackings, estos crackers, ¿no? Ahora, el nafta y los productos más pesados también producen muchas olefinas, pero no es tan limpio. Ahí sí es mucho más dificultoso separar los productos que forman. Entonces hay más contaminación de CO2, de hidrógeno, que crea un problema también, porque explota a esas temperaturas radicalmente. Entonces sí, nosotros estamos viendo en otras posibilidades, otros mecanismos de cómo crear olefinas que sean útiles directamente del alcano, selectivamente. Más que todo es la selectividad.
Gracias. ¿Alguna otra pregunta o comentario? Si no, agradezcamos nuevamente al profesor Mindiola por su
Gracias.
presentación. Tengo ahora el gusto de presentarles al profesor David Chenovet. David was born in Indiana and received his bachelor's degree in chemistry from Indiana University, Purdue University, Indianapolis. After graduation, he completed an internship in organic chemistry at Dow AgroSciences Prior to joining the Neurosciences Discovery Chemistry Research Department at Eli Lilly in the year 2000. David left Eli Lilly and headed to Caltech in 2003 to pursue a PhD degree with Professor Peter Dervan. After graduation in the year 2009, he moved to MIT to work with Professor Timothy Swager as a National Institutes of Health postdoctoral fellow. David was appointed assistant professor in the Department of Chemistry at the University of Pennsylvania in the year 2011 in the Biochemistry and Molecular Biophysics graduate group in the Perelman School of Medicine in 2013 and in the Bioengineering graduate group in the School of Engineering and Applied Science in 2013. Today, David will be telling us about the rational redesign of the collagen triple helix interface. Please.
Okay, thanks so much for the introduction, and thanks for the invitation to come and tell you about some of our science. It's a pleasure to be in Mexico City. It's a beautiful city, and this is one of the pictures that we took last night looking off the balcony on the 6th floor of the hotel. So, very beautiful city. Today, I want to start by telling you a little bit about my research group. So we started about 6 years ago at University of Pennsylvania, and we work in several diverse areas. So primarily, we build molecules, but we build molecules for applications in several areas of science. One application is targeting the structure and function of RNA. So we think that we can develop small molecules to target disease states at the RNA level. The other area is developing chemical tools to probe biology. And what I'm going to tell you about today is engineering biomolecules, and specifically engineering this molecule right here, collagen. And I'm going to tell you about a simple approach that we took and primarily focus on a one-atom substitution from carbon to nitrogen. But first, I want to tell you a little bit of, give you a little bit of background on collagen. So this is my first graduate student who started working on this project back in 2011, Yitao Zhang. And his project was focused on engineering the peptide backbone of the collagen peptide sequence here, which is often a X amino acid, Y amino acid, and glycine repeat sequence. So collagen, collagen has a lot of biological importance. It's the main structural protein in the animal kingdom. I would say about 1/3 of our body weight is actually collagen, and about 2/3 of the dry weight of our skin is collagen, composed of collagen. It occurs in tendons, ligaments, skin, our fingernails, our toenails, everywhere. Collagen's all over the place. It's been used as a biomaterial for bone grafts, for cosmetic surgery, for burn surgery, tissue regeneration, and mutations in this amino acid sequence in collagen. They form the molecular basis of many genetic diseases, such as osteogenesis imperfecta, also known as brittle bone disease. There's a lot of early work that's been done on the structure and packing of collagen by greats such as Pauling and Ramachandran, Crick, Rich, Yonath, and many more. And then many synthetic modifications to the collagen peptide structure have been made with this goal of engineering the properties or the biomaterial properties of collagen peptides for use in other applications. And primarily, a lot of the synthetic work or synthetic modifications have been done by the Rains group. I want to give you just a little bit of a broad background on collagen and the occurrence. So the earliest known use of collagen dates back to 8300 BC, where it was used in waterproof coatings and skull decorations, also in utensil production. It was used as glues and as a glue in ancient Egypt. Native Americans used this, in many different uses. It was used in early China and Greece, and 1400 to 1700 AD, we see use primarily emerging in furniture and binders for paints and different types of practical materials uses. So everywhere from adhesives to food, construction and repair, painting and decoration, and materials coatings. But we really didn't see the emergence of it as a biomaterial until the early 1800s. So back in about 1881, Lister and this other physician here, they started realizing that this could be used as a biodegradable suture material. And so here we see one of the early formulations of catgut and oil, which was used as a suture for surgeons. The nice thing about this is they could sew up a wound, and then it would degrade as the wound was healing, and they didn't have to go back and take it out later. This right here is this is rat tail collagen, and so if we just take the tail of a rat, we cut it and we pull on it, we can see that we get this fibrous material out of here, which can be used in sutures and things like this. So this is collagen. These are all pure collagen fibers. Same thing with a kangaroo tail, or any other animal like that has a tail. So if we look at modern applications of collagen, so modern applications in biomedicine range from wound treatments, 3D cell cultures, contact lenses, root canal fillings even. And almost every major pharmaceutical company has some formulation for collagen. So here's collagen sponges that are used for wound healing, where we can take collagen sponges, we can soak them with antibiotics, we can put them on a wound, and then we can prevent infection as that wound is healing. There's all kinds of uses. Also shampoos and cosmetics, sausage casings, glue, everything you can imagine. Collagen's been used for probably. There are several different biomaterials companies that use collagen. A lot of commercial efforts to commercialize collagen. Here's Collagen Matrix, a company that we're starting to work with. Collagen Solutions, another company we're starting to work with. This is a very interesting startup that we're just starting to talk to about collaborations, Modern Meadow. So they're interested in making synthetic collagen so that they can use it to make synthetic leather materials. So they want to make recombinant collagen from E. coli and then turn it into leather so that they don't have to use animal hides for leather production. So another interesting application. Collagen in Mexico. So another really interesting use of collagen is in archaeology. So collagen's been used to date artifacts and antiquities back to early times. So here's an example of early knife blades from Mexico, and they were able to, based on the collagen residue that was left on this, they were able to date these back to 1,000 years prior to the Aztecs and the use of these in sacrificial ceremonies. So other uses of collagen in Mexican industry, the leather and tanning for footwear and upholstery industries, cosmetics, and if we just look at biomaterials growth in Mexico between 2011 and 2015, that grew by about 39.5% and comprises about a total of 4% of all Mexican exports for biomaterials. So the materials properties of collagen are also very interesting. So there's these unique characteristics of collagen that's treated chemically, where you can give collagen a rubbery or elastic consistency. If we plot proteinaceous biomaterials in green here, and we plot their strength versus their stretch, we find that collagen falls right in the middle. The hardest materials up here, you see diamond. Down here, you see elastin, which is very stretchy. So we're interested in being able to modulate the properties of collagen so we can shift this point right here where collagen falls to other areas on this chart so we can get new materials uses out of it. There's about 29 different types of collagen that have been identified. And the distribution in vivo ranges from skin to blood vessels to tendon to bone. If we zoom in and look at the structure of collagen, at its most fundamental level, collagen's composed of a triple helix of 3 peptides. So these 3 peptides wrap around each other. Each is a left-handed helix that then wraps around the other 2 collagen peptides to form an overall right-handed helix. And that right-handed helix makes the fundamental building block for almost all collagen materials or fibrous collagen materials that we see in nature. If we then take these triple helical peptides that assemble, we can take those and cross-link them into a network that forms a higher order biomaterial. And then if we zoom in here, say on a cross-section of skin, we can see the structure of this banding structure that comes from the self-assembly of collagen around the 500 nanometer size limit here. So here's a electron density map of what that looks like assembled into a fiber. Just another interesting look at collagen in bone. So all of our bones contain collagen. If we zoom in to bone and look at the hierarchical structure, we can see that as we funnel down to the most basic building blocks or most basic material that bone's composed of, it's actually a collagen peptide at this level that assembles into a triple helix, and again, just like in skin, that then self-assembles into a material that becomes calcified and dehydrated to form the fundamental material that makes up bone. If we zoom in on a tendon, so here's a tendon, we pull the fibers apart in a tendon, we can eventually get all the way down to what is a triple helix of collagen at the most basic level, which is these 3 peptide chains. So if we look at early structural work, so back in the 50s, scientists like Pauling were trying to figure out what collagen actually looked like, what its overall structure looked like, or its overall protein structure looked like. So this is a notebook page from Linus Pauling, dated 1951, where he was just basically doing some speculative model building and trying to figure out what the overall structure or the basic fundamental building block of collagen looked like. Here you can see he's got 3 strands drawn. So he was able to deduce that collagen's made up of 3 peptide strands. Here he was just sketching out the peptide backbone and trying to figure out how those 3 strands went together. You can see he's got the peptide backbone drawn here, he's got a proline here, and he's drawing hydrogen bonds between the donors and acceptors of the peptide backbone. So it turns out he actually got this wrong. He got a lot of things right, but Pauling got this one wrong. He's got too many hydrogen bonds in here at the expense of putting in cis-amides. So it turns out there's no cis-amides, and there's 1 fewer hydrogen bond per 3 amino acids, which will become important later. So here, if we look at those three peptides and how they line up and register with each other, it turns out there's a 1 amino acid phase shift in each of the peptide chains. And that allows formation of a hydrogen bond, a single hydrogen bond from the glycine of 1 strand to the carbonyl that's between the X and Y residue of the next strand. And then another 1 amino acid phase shift, and this glycine lines up for a hydrogen bond with the carbonyl between these 2 X and Y residues. And that's what serves to link these 3 strands together at the hydrophobic interface of the triple helix. So here's just an overall triple helix structure with each strand colored differently. If you look at this repeat sequence, it's always glycine flanked by an X and a Y amino acid, which can vary. And the variation in that X and Y amino acid allows for interaction with different proteins in the body. But this glycine here, no matter what, if it's in vertebrates, if it's in bacteria, if it's in viruses, the glycine's always strictly conserved in the 3rd amino acid position in the repeat sequence. Here's just lining up the gene sequence from human, mouse, chicken, dog, and you can see the glycines are colored in blue and they repeat every 3rd amino acid here. And then we see a lot of variation in the other sequence. So if we think about beyond collagen just being used as a structural material, it turns out it also undergoes a host of protein-protein interactions in the body that are important for all kinds of diseases, ranging from fibrotic diseases to cancer. So here's a snapshot of 3 different types of collagen and their interaction with different proteins in the body. You can see there's a wide range of proteins that collagen interacts with based on that variation in the X and Y sequence. Some of those are important therapeutic targets for cancer and fibrotic disease. So this one right here, matrix metalloprotein 1, that's an important cancer target. HSP47, that's another protein that it interacts with, and that's an important target for fibrotic disease. We have high-resolution crystal structures of some of these interactions and how the proteins contact collagen. Here's just a few of those from the protein data bank. We see in tan, this is our collagen triple helix, and in blue, each of these shows a different protein and how it interacts with collagen. And the interesting thing, the interesting take-home message from this slide is that protein-protein interactions with collagen are very diverse. So here's a protein that interacts with just a couple amino acids on the side of collagen. Here's one that interacts as a homodimer, as a large composite surface, and it covers one whole side of the collagen triple helix. Here's another one that homodimerizes and almost covers the entire triple helix on both sides. So this is HSP47, which is an important therapeutic target for fibrotic disease. This MMP is another important therapeutic target for cancer. Okay, so let's look at Yitao's project. So Yitao, when he started as a grad student, when I first started at Penn, his project was to go through this collagen backbone and analyze a crystal structure that was in the protein data bank and look to see where we could make synthetic modifications to enhance the properties of collagen. So the goal was to be able to make triple helical peptides that would assemble, that would have higher thermal stability or would have new properties. So here's where Yitao started. He made this 21 amino acid peptide that was already reported in the literature as just a control collagen peptide. So it was known that you could make this, you could synthesize this peptide just by solid phase synthesis techniques. So this is a repeat of proline, hydroxyproline, glycine 7 times. If you make this peptide and you let it stand in solution at a certain concentration, that'll spontaneously assemble into a triple helix, which looks like this up here. When that assembles into that triple helical structure, you can take a CD spectrum of it, and there's a characteristic CD signature that looks like this, with a negative peak here and a positive peak at about 220 nanometers. You can then heat this up, and you can lock on any of these points in the CD spectrum, and you can watch the cooperative unfolding of this triple helix. So basically, you can watch that whole triple helix come apart and then go back together reversibly. And if you look at the inflection point here, that's the melting temperature for unfolding that triple helix, right? When 50% of it's unfolded, that's the TM. And so that's going to be the parameter that we look at when we put unnatural amino acids in here to see if we've actually stabilized the triple helix. But we can also look at the CD spectrum. We can heat this up and unfold the whole triple helix, and then monitor the CD as it refolds. And we can look at the kinetic refolding of the triple helix and see how fast it refolds. And then we can characterize whether or not it really is a triple helix with techniques like size exclusion chromatography coupled with multi-angle light scattering or analytical ultracentrifugation. So those are the techniques that we have at hand to use to characterize the self-assembly of this peptide. So here's what we did. We looked at a crystal structure of the collagen triple helix. We zoomed in, we looked at the peptide backbone, and we thought about modifications in this backbone that we could make that would add new weak interactions. So this glycine residue right here, that's the only residue that's never been able to be replaced in collagen for another amino acid. So what we did is we thought about, what if we don't replace the hydrogens here with a side chain, which would be too bulky? What if we replace the carbon atom with another atom? Specifically, if we replace the carbon atom with a nitrogen atom, and we model that in, it looked like it should make one extra hydrogen bond. And so this could be that extra hydrogen bond that Pauling proposed that might actually glue this triple helix together even better than with one cross-strand hydrogen bond. So here's the canonical hydrogen bond right here in the collagen triple helix, and here's the one that we're going to add. So Yitao made a new peptide to compare against his control peptide, where he just simply replaced the carbon atom with a single nitrogen atom, and then looked to see what the effect of that would be. He also replaced the carbon atom of the X position here and the Y position right here to see what the effect would be. So from the crystal structure, we had 3 hypotheses about those 3 modifications. The first was in the X position here in the middle. So if we replaced the carbon atom of this proline and we modeled that in, we thought that that would result in a solvent-exposed nitrogen lone pair, and that should be just fine, and the peptide should still self-assemble into a triple helix. In this position right here, in the Y position, when we modeled in the replacement of a nitrogen for a carbon atom, the lone pair looked as if it would make a lone pair interaction across the triple helix, and that should be destabilizing. So that should not form a triple helix. And then, as I showed you before, when we replace the carbon atom of glycine with the nitrogen, that's what should be stabilizing and form our extra hydrogen bond. So what I did is I plotted a melting temperature scale here for you. This green line is our peptide right here. 40 degrees is where that triple helix comes apart. That's the inflection point. And so now what we're going to do is look at this modification and see where they fall relative to this control peptide. So it turns out this one right here indeed still forms a collagen triple helix, and it's just as stable as the control peptide. So it unfolds at 40 degrees. This one, as we predicted with the lone pair interaction, it's destabilized and it doesn't form a collagen triple helix. Now, the last one left is replacing the glycine. So when we replaced the glycine, we were excited to see that that actually adds stability. That adds 11 degrees in thermal stability with just a single atom substitution. So one hydrogen bond donor is worth quite a bit in the context of this 21 amino acid peptide. So the obvious thing, the obvious next step, is to add 2 and see what the effect would be. So we added 2. So now there's we call this azoglycine. That's what's replacing glycine. So we added an azoglycine here instead of glycine, and we added another azoglycine adjacent to that. And when we did that, we saw the thermal stability go up almost double. So it went up just above 60 degrees. So that was worth about 11 degrees. This is worth about another 10 degrees when we add 2. So it's looking as if every single atom substitution adds about 10 degrees in thermal stability. And then we spaced those a little bit further apart, and the stability went down just a little bit. Then we added 3. And when we added 3, we found that, again, it's still additive. And the thermal stability went up. And now we're almost to 75 degrees here for that melting temperature. And again, when we skip space those, instead of having them in adjacent triplets, it's a little bit destabilizing. So the next thing we did is we actually cut this peptide down to a shorter fragment to see what the smallest peptide we could make would be that would still self-assemble into a collagen triple helix. So here's the one that we have right now with 3 in it, and that's about 75 degrees. And if we now chop this down to a 12 amino acid peptide with all azoglycines, we're still at about the same melting temperature as the 21 amino acid collagen peptide that we started with, except we're about half the size. And then if we add just one more triplet on there, we're now at 15 residues. We're up at about 80 degrees for the thermal stability of that triple helix. So if you take that nitrogen replacement and you vary the position along the collagen chain, you vary the increase in temperature by anywhere from plus 11 degrees in thermal stability to 7 at this end and 6 at this end. And so that's because most helical biopolymers, when they're assembled, they fray a little bit at the ends. They're held together tight in the center, but at the ends you're getting a little bit of fraying. And so the energetic benefit is not quite as good at the end. If we then look at the multiple substitutions, this is where the effect becomes additive, and we can add up to 34 degrees with this one here. And then these are the shorter. This is a summary of the shorter variants, where this is the 12 amino acid and this is the 15 amino acid peptide. You can see these also refold much faster than a normal collagen triple helix or our control sequence. So these kinetically refold faster. If we take a look at standard collagen peptides, you would need 45 amino acids from a standard collagen peptide or from a natural peptide sequence to get a collagen triple helix that would be stable up to 80 degrees, and here we can do it with just 15 amino acids. So now the question is, we've re-engineered the interface of this collagen triple helix to be more stable, to endow it with better properties or more stability. Now, does it interact with biology in the same way with these proteins? So that's the next question we wanted to address. So we started looking at this, the collagen sequence that codes for this interaction with HSP47, this target for fibrotic disease. So it turns out the pro-arginine glycine sequence is what codes for this interaction with the protein. So that's an important sequence for binding this protein. So what we did is we made a peptide now where in the center we've replaced one hydroxyproline with this arginine. And then we again did the same experiment where we made a single atom substitution from carbon to nitrogen, and we looked to see if that would be stabilizing when paired next to this arginine residue. So here's unfolding of the control peptide, and here's unfolding of this peptide now with the extra hydrogen bond. So indeed, it looks like it's a general effect, and it's stabilizing even when paired next to a different amino acid here. And it refolds much faster. So we've done several computational studies, molecular dynamic studies on this azoglycine-containing collagen peptide, and I'm just going to skip past those to the next slide. Basically, what we can see is that this extra NH that we've added here, it can form a hydrogen bond between two different carbonyls, and at a higher temperature, it can actually flip back and forth between these two carbonyls. We can measure hydrogen bonding parameters, distances, and angles, and we can see that this falls right within the gray area here that you would expect for the angles for a strong hydrogen bond and for the distances for a strong hydrogen bond. We've also recently been able to crystallize this peptide and get a high-resolution structure of what it looks like so that we can see this extra hydrogen bond. So this is now a crystal structure of a full collagen triple helix that contains this azoglycine residue at 1.1 angstrom resolution. This is how it packs. All of these aqua spheres here are the water molecules that are solvating the collagen triple helix. And then if we zoom in here, this is a movie of the electron density map for that crystal structure that we obtained that has that extra azoglycine in it. So this dark blue atom right here is the nitrogen that we've swapped out for the carbon atom that used to be there. You can see that that forms an extra hydrogen bond from one peptide to a carbonyl on the next peptide, but every peptide in that triple helix assembly contributes an extra hydrogen bond donor. So there's there's a network of hydrogen bonds formed in here. So now instead of just the 3 canonical hydrogen bonds, there's actually 6 right here for a single atom replacement. And if we take a slice through the collagen triple helix and we look at the 3 residues that are interacting with that glycine, this is the canonical hydrogen bond that was there before, and this is the one that we just added right here. If we then plot the hydrogen bond parameters for the canonical hydrogen bond and the one that we just added, as far as distance and angle against all other hydrogen bonds in collagen crystal structures in the protein data bank, those are all in gray. You can see that each of these dots for our new hydrogen bond, those are labeled in red right here, they fall right within standard hydrogen bonding parameters. If we then I'll skip this. If we then take our crystal structure and we align the backbone with a crystal structure from the protein data bank that doesn't have this azogly substitution in it, we can see the RMS deviation for all atoms is pretty small. It's about 0.78 angstrom. And then if we compare the Ramachandran plot or the Ramachandran angles of glycine to azoglycine, we can see that this azoglycine is a near perfect mimic for glycine as far as the Ramachandran plot's concerned. So now, does it actually interact with this protein in the same way? Does it recognize biology in the same way? So there's a simple experiment that we can do. We buy recombinant human HSP47. This has 5 tryptophans in this protein. When it homodimerizes around collagen, we can see those tryptophans quench as they change orientation. And so we can extract a KD from this, or a binding constant from this, as we titrate collagen in. So we did that experiment with our control collagen peptide, and with our azacylglycogen peptide, and it turns out they bind in exactly the same way. So this tells us that from the protein-protein interaction standpoint, the overall topology of this collagen triple helix hasn't been changed at all. Now the next thing we did is we looked at a different protein. So it turns out matrix metalloproteins are collagenase enzymes. They're very important for regulating collagen in biology, and they serve to degrade the collagen triple helix. So we wondered if collagenase enzymes would actually degrade and cleave our peptide in the same way that it will collagen. So what we did is we bought these collagenase enzymes from Clostridium. They're used for tissue dissociation. They're very aggressive enzymes that'll just indiscriminately chop collagen peptides. And we exposed our collagen peptides to those to see if they were resistant to degradation. So here again is our control peptide. When you expose that to collagenase enzymes, you see it's rapidly degraded. And you can follow a two-dimensional plot of the CD spectrum, and you can see the CD peaks indicative of a collagen triple helix degrade over time. When we do that same experiment with an azacylglycan-containing collagen peptide, we see no degradation at all. The enzymes just don't cleave it. And so now the question is, does the enzyme interact with the collagen peptide, or does it just not interact at all? Does it just leave it alone? So what we did is we took our collagen peptide that contains azaglycine, we spiked it back into the reaction where we know the collagenase enzymes will degrade this peptide, and we looked to see if there would be an inhibitory or a protective effect over the collagen peptide that we know gets degraded. So here's that data. You can see rapid degradation here in the blue line of this collagen peptide, and as we increase the concentration of our azacylglycan-containing collagen peptide, you can see we get a complete protective effect. So now that's on a model system or on a collagen peptide. So in the context of a collagen biomaterial, we wanted to do the same experiment. So we bought recombinant collagen 3, which is used to make biomaterials. We exposed it to collagenase enzymes. We see rapid degradation of collagen 3, and then we added a half an equivalent of our peptide, and again we see a protective effect where there's no degradation of the collagen 3. So this is useful because now we can think about using these peptides to tune the degradation rates of different collagen biomaterials that are used in medicine. And so now what we're thinking about is using these peptides as protein-protein interaction modulators for different therapeutic uses in the collagen interactome. We're thinking about using them in wound healing applications, using them to modulate the collagen material properties, as I showed you before here, and in tools for biology and structural biology. Okay, and the most important slide, I need to thank all the people in my lab that have worked on these projects over the years. Several students, my first students here who have graduated, Stephanie Barrows, Mai Tran, and especially Yitao Zhang, who worked on this project. They're all three in their postdocs. There's 4 more students getting ready to graduate. I'd like to thank these funding agencies here and a lot of fantastic collaborators at Penn, too. And I'd like to thank you for your attention and take any questions that you have.
Thank you very much for a very interesting presentation. Si tienen preguntas o comentarios, por favor.
Hi, thank you for your talk and welcome to Mexico. I was wondering how the scientists could identify the collagen in this black stone that is almost 500 years old. And how about the protein degradation?
Yeah, so I think, so you could imagine using electron microscopy, or you could extract something off of the surface and then use mass spec. You could also use isotope dating to date the age of the residue that's on there. So primarily mass spec techniques and isotope ratios.
Well, also, how about the degradation of the protein? It's almost 500 years old of, well, this pre-Hispanic stone is almost 500 years old. My question is, how about the protein degradation?
Yeah, why is it still left on there?
Uh-huh.
Yeah, you still have some residue that contains some of it. It's protected in some way. It hasn't fully degraded.
Okay. Thank you.
Dr. David, good afternoon. Welcome to Mexico.
Thank you.
What is the benefits or secondary consequence that to take collagen by meal supplement?
As a supplement. Yeah, that's a great question. You start to see a lot of advertising in nutraceuticals and all these different products for collagen supplements. I'm not sure that it actually makes it through the stomach and doesn't get broken down. I'm not sure how well it would distribute. So I can't really comment on whether or not that works or not. Yeah, I don't know. Now, collagen does get chopped down into smaller peptides, and some of those smaller peptides have a lot of bioactivity too. So maybe it's through a smaller fragment that gets chopped down, and then there's, you know, bioactive components that are beneficial in some way. But, yeah.
¿Alguna otra pregunta o comentario? Bueno, a ver, una más, sí.
Buenas tardes.
Thank you.
Felicidades por su conferencia. Es muy interesante.
Oh, I don't have where? Yeah.
Buenas tardes. Felicidades por su conferencia, muy interesante. Habló sobre el beneficio en diferentes cosas, de comida, de química, múltiples usos del colágeno, ¿sí? Entonces, mi pregunta es, hay muchos artículos, muchos productos hechos con colágeno en relación a faciales, productos faciales, para regenerar la piel. ¿Qué tanto la regenera? ¿Un 50%, un 10%? ¿O realmente no regenera nada? Por ejemplo, las cremas, los labiales, los aceites que se inyectan en la boca, no sé, todo eso. Gracias.
So, okay, should I take this off? Yeah. So collagen's been used for injectable uses for some time, and we know it's biocompatible and it can be used for those applications. As far as topical applications and skin regeneration and things like this, for wound healing and burns and things, it actually does help, and it's been used in several medical uses by physicians for that for some time. The products that are sold over the counter, though, and creams and lotions and things, I really can't speak to how good those are, or whether or not there is any benefit from it. I'm not sure, actually. Some of the claims may be true, some may be, a little overhyped.
Muy bien, pues si no hay más preguntas, agradezcamos nuevamente. Y pues muchas gracias por su asistencia y continuamos, no se olviden, a las 3:30.